Those glittering star clusters are not what they seem. They are ancient cities of suns, bound by gravity for billions of years, and within them, our most fundamental rules of the cosmos break down. By the end of this journey, you will see the universe through a lens of profound and beautiful mystery. We are about to explore 50 discoveries from these stellar archives that defy explanation, from stars that murder their companions to planets that should not exist. How can a group of stars born together hold such wildly different secrets? What does it mean when the oldest structures we know act in ways physics cannot yet describe? This is a voyage to the edge of our understanding. What do you believe is waiting for us in that ancient light? Our first discovery is a stellar murder mystery. Deep within the ancient globular cluster known as M5, a cosmic predator is at work. Astronomers found a pulsar, the spinning corpse of a massive star, locked in a deadly dance with a tiny, doomed companion. This pulsar earned the name Black Widow for a chilling reason. It is actively consuming its partner. The pulsar's intense radiation and powerful particle winds are relentlessly stripping material from the smaller star, vaporizing it into oblivion. This process unleashes a torrent of the universe's most energetic light, gamma rays and X-rays, a beacon of destruction visible across thousands of light years. This system is not just a curiosity, it is a profound challenge. In the serene, ancient neighborhoods of globular clusters where stars are densely packed, such violent relationships were thought to be rare or short-lived. The existence of this Black Widow suggests our models of how stars interact in these crowded cities are incomplete. How does such a system form and survive without being torn apart by another passing star? It forces us to rewrite the rules of stellar evolution under extreme conditions. This pulsar and its victim have become a natural, if terrifying, laboratory. Here, we can observe physics pushed to its limits, where gravity and radiation battle in a spectacle that reveals the raw, destructive power hidden within the universe's oldest communities. That same destructive power may have forged something even more miraculous. In the neighboring ancient city of stars, globular cluster M4, astronomers found an impossibility. A planet, not just any world, but one orbiting the corpse of a star, a pulsar, in a place where planets were thought to be utterly impossible. This world, known as PSRB 1620-26b, is a survivor from a cosmic catastrophe. Picture the environment. The cluster is over 12 billion years old, formed when the universe itself was in its infancy. The space between stars is flooded with intense radiation from countless stellar explosions and dead stars. Any normal, dusty planet forming disk around a young sun would have been ripped apart by the gravitational tides of passing stars eons ago. So how is this planet here? The leading theory is one of stellar resurrection. This is not a first-generation world. It is likely a second-generation planet born from absolute destruction. The story goes like this. The pulsar it orbits was once part of a binary system. Its companion star aged, swelled into a red giant, and was then utterly shredded by the pulsar's gravity. The debris from this stellar murder did not just vanish. Instead, it formed a new, thin disk of hot gas and dust right around the pulsar. From the ashes of one star, a new world coalesced. This means the planet is made from the heavy elements forged in the heart of a dying sun, a literal diamond born from stellar rubble. Its existence forces us to expand our definition of where life could potentially arise. If planets can form in the aftermath of stellar death, in the most hostile neighborhoods imaginable, then the recipe for building worlds is far more resilient and creative than we ever dreamed. What other impossible survivors might be hiding in the ancient glow of these clusters? Yet the very concept of a second-generation world leads us to an even deeper puzzle within these ancient stellar cities. Among the cool, ancient red stars that dominate globular clusters, astronomers keep finding brilliant, hot blue stars shining where they simply do not belong. They are called blue stragglers, and their existence is a direct affront to everything we know about how stars age. In a cluster where every star was born from the same primordial cloud over 12 billion years ago, they should all be at similar advanced stages of life. The massive, hot blue stars should have burned out and died eons ago. So what are these vibrant, youthful-looking stars doing there? They are stragglers, lagging behind in the aging process, glowing with a fierce blue light that signals immense heat and a relatively short remaining lifespan. How did they get this way? The leading theories are as dramatic as they are violent. The first possibility is a stellar collision. In the densely packed core of a globular cluster, stars can swing so close to one another that they do not just pass by, they slam together. Two older, cooler stars merge into a single, more massive and hotter star, effectively hitting the cosmic reset button on their evolution. The second possibility is a slower, more intimate theft. In a binary star system, one star can siphon hydrogen fuel from its companion over millions of years. This stolen fuel rejuvenates the thief, making it hotter, brighter, and bluer, while its donor star is left as a depleted, faint remnant. The third possibility is that two stars in a tight binary pair eventually spiral inward and merge, creating a single, more massive blue star. Each of these processes creates a stellar imposter, a star that looks young but is actually a Frankenstein's monster built from ancient parts. Their presence forces us to see these quiet, ancient clusters not as serene retirement homes for stars, but as dynamic arenas of constant gravitational interaction, where stellar lives are rewritten through catastrophe and theft. They are the ultimate cosmic outliers, living proof that even in the oldest neighborhoods, chaos and renewal are always at work. The youthful imposters known as blue stragglers reveal a startling truth about stellar evolution, but what happens when the stars that should be there simply vanish? This brings us to a discovery that is not about what we see, but about what we do not see. In some of the most ancient globular clusters, astronomers face a ghost problem, a deficit of red giant stars. Based on our well-tested models of how stars age, we should see a predictable number of these swollen, cool, elderly stars in every old cluster. They are a natural and expected phase of life for sun-like stars after they exhaust the hydrogen fuel in their cores. Yet in certain clusters, the red giant branch, as it is called, looks strangely sparse. It is as if you entered a retirement community and found far fewer elderly residents than the birth records suggest should be there. Where did the giants go? This missing giants problem points to a fundamental gap in our understanding. One compelling explanation is that in the unique environment of these dense clusters, low-mass stars are losing weight far more dramatically than we thought possible. Imagine a star as it begins to puff up into a red giant, having its outer layers literally stripped away by the relentless gravitational tides of passing neighbors or by the intense radiation bathing the cluster core. This extreme mass loss could prematurely end the red giant phase, causing the star to skip its grand final act and transition directly to a faint helium-burning phase or a white dwarf, effectively hiding in plain sight. The other, more unsettling possibility is that our standard models of stellar evolution, which work so well for isolated stars, are incomplete for stars living their entire lives in these extreme, crowded cities. The constant gravitational nudges, the different chemical soup they formed from, or some other cluster-specific factor might alter their internal nuclear furnaces in ways we have not yet accounted for. This absence is a powerful reminder that sometimes the most important clues in cosmic detective work are the empty spaces, the expected guests that never arrived, forcing us to question the very timelines we have written for the lives of stars. The absence of expected stars is a silent clue, but the motion of the ones we can see tells a louder, more contentious story. This leads us directly into one of the most heated debates in modern astronomy, the dark matter controversy within globular clusters themselves. For decades, dark matter has been the invisible glue holding galaxies together, its gravitational pull dictating the speed at which stars orbit galactic centers. So when scientists looked at the dense knots of stars in globular clusters, they naturally asked, does this mysterious substance bind these ancient cities too? Initial observations of stellar motions within some clusters seemed to hint at a yes. The speeds at which stars were whirling around a cluster's core appeared, in some cases, to be slightly too fast to be explained by the gravitational pull of all the visible stars alone. It was as if an unseen hand was adding extra weight, keeping the stellar city from flying apart. This sparked a fascinating possibility that globular clusters could be miniature dark matter halos, offering a nearby, simpler laboratory to study this cosmic phantom. But the universe loves a good plot twist. More recent and precise studies using advanced telescopes and sophisticated computer simulations have turned that idea on its head. The overwhelming consensus now is that most globular clusters are actually remarkably clean of dark matter. The stellar motions that puzzled astronomers are now largely explained by the complex gravitational dance of the stars themselves, a dance that evolves over billions of years. As stars interact, they slingshot each other, with lighter stars getting ejected to the cluster's outskirts while heavier stars sink to the core. This dynamic process, called mass segregation, creates a gravitational environment that can mimic the presence of extra, unseen mass. So the verdict for now is that these clusters are built almost entirely from what we can see, stars and the remnants of stars. This makes them profoundly unique. They are essentially pure gravitational laboratories, systems where the rules of gravity, as described by Newton and Einstein, can be tested without the complicating fog of dark matter. If any anomaly in stellar motion persists, it might not point to an invisible substance, but to a subtle flaw in our understanding of gravity itself in these extreme, crowded conditions. The clusters, therefore, stand as pristine cosmic experiments, challenging us to see if our fundamental laws hold true in a city made of light alone. If globular clusters are pristine gravity labs, they also possess a cosmic catapult capable of launching stars into the great dark beyond. Astronomers have tracked stars moving so fast they are not just leaving their home cluster, they are escaping the Milky Way galaxy entirely. These are hypervelocity stars, stellar projectiles rocketing through intergalactic space at speeds exceeding 1 million miles per hour. Their origin story is written in the frantic core of a dense star cluster. The most likely launch mechanism involves a gravitational slingshot of breathtaking precision. Imagine a tight binary star system, two suns orbiting one another, wandering too close to the supermassive black hole that lurks at the center of our galaxy. In a violent gravitational tango, the black hole's immense pull can capture one star while violently flinging its companion away at an astonishing speed, like a stone from a sling. While this often involves the galactic center's black hole, a similar, though less powerful, ejection can happen within the cluster itself through complex multi-star interactions. In the crowded core, a close encounter between two binary systems can disrupt their delicate orbits. Through this gravitational chaos, one star can be accelerated to such an extreme velocity that the cluster's gravity can no longer hold it. It is shot out like a bullet, destined to wander the lonely voids between galaxies. The discovery of these runaway stars does more than add a dramatic escape narrative. Each hypervelocity star is a forensic tracer. By calculating its speed and tracing its path backward across the sky, astronomers can pinpoint its likely birthplace, often leading right back to a specific globular cluster. This gives us a powerful tool to map the hidden gravitational landscape of these dense environments and to test our models of how stars interact in such extreme traffic. These stellar exiles carry the chemical signature of their home cluster with them, offering a rare sample that we can study up close, a messenger from an ancient city we can no longer see. Their very existence proves that globular clusters are not just serene islands, they are active engines capable of manufacturing the fastest solitary objects in our entire galaxy. These stellar exiles carry a chemical fingerprint, a hidden record of their birthplace. That record reveals an even stranger secret within the clusters themselves, a kind of cosmic contamination. Astronomers peering into the hearts of globular clusters found stars that are chemically polluted. This is not dirt or dust, but a fundamental alteration in their elemental recipe. Within a single cluster, stars that should be identical twins, born from the same primordial cloud, show shocking differences. Some stars are rich in elements like sodium and aluminum, while others show a severe depletion of oxygen and magnesium. This is the multiple population phenomenon, and it shatters the old idea that a globular cluster is a simple one-generation family. How can stars from the same birthplace have such different chemistry? The leading theory paints a dramatic picture of the cluster's youth. Imagine the first generation of massive stars igniting in a dense, young cluster. These titans lived fast and died young, ending their lives in colossal supernova explosions. But crucially, not all first-generation stars explode. The moderately massive ones, perhaps 8 to 10 times the mass of our Sun, end their lives in a less violent but more polluting way. They shed their outer layers in intense stellar winds, flooding the cluster's interior with processed gas. This gas is not pristine. It is enriched with the byproducts of nuclear fusion from deep within these stars, elements like sodium and aluminum, and it is depleted of others like oxygen that were consumed as fuel. Then a second wave of star formation begins. This new generation condenses from a toxic soup, a mix of the original primordial gas and this newly polluted material. Stars born from this contaminated cloud carry the chemical signature of their predecessors. This means the serene, ancient cluster we see today is actually a fossil of a tumultuous two-act drama. It is not a single burst of creation, but a staggered process where the death of the first stars directly shaped the birth of the next. The polluted stars are therefore the children of the cluster's own internal cycle of life and death. This discovery forces us to see these structures not as static snapshots, but as dynamic ecosystems with a complex history written in the very atoms of their stars. What other stories of cosmic recycling are locked within their ancient light? The chemical pollution within our own galaxy's clusters hints at a complex history, but to truly understand their origins, we must look beyond the Milky Way. In our nearest large galactic neighbor, the Andromeda Galaxy, astronomers have made a startling find: clusters that defy the very definition of what a globular cluster should be. Scattered throughout Andromeda are stellar collections that look and act like classic globular clusters, dense balls of hundreds of thousands of stars, but they shine with a brilliant, youthful blue light. Spectroscopy reveals their secret: they are only 1 to 3 billion years old. This is a cosmic shock. In our own galaxy, globular clusters are universally ancient, fossils from the universe's first few billion years. Finding such young, massive clusters in Andromeda forces a profound question. Are globular clusters always ancient relics, or can they form at any time in a galaxy's life? This discovery directly challenges the long-held idea that globular cluster formation was a single, special event tied exclusively to the chaotic early universe. It suggests that the recipe for building these dense stellar cities is not lost to time. The right conditions, perhaps a period of intense star formation triggered by a galactic merger or a massive inflow of gas, can apparently cook up new globular clusters even in a mature galaxy like Andromeda. This opens up a fascinating possibility. What we classify as a globular cluster based on its shape and density might actually be the end product of several different formation pathways. Some are truly primordial, dating back to the dawn of galaxies. Others might be the reinforced cores of devoured dwarf galaxies. And now we know that some are simply late bloomers, born from more recent, violent episodes in a galaxy's history. The existence of these young clusters in Andromeda turns them from simple fossils into active diagnostic tools. By comparing their numbers, locations, and chemistry to the ancient ones, astronomers can read the recent chapter of Andromeda's biography, uncovering tales of collisions and bursts of star formation that happened long after our own Milky Way settled into a quieter life. It reveals that the story of globular clusters is not a closed book from the distant past, but an ongoing narrative, with new chapters being written in galaxies across the cosmos. These young clusters in Andromeda are a testament to ongoing creation, yet even the oldest clusters are not static islands. They are slowly, inexorably being unraveled by the galaxy itself. Wrapped around many globular clusters are faint, ethereal rivers of stars, stretching for thousands of light years across the galactic halo. These are tidal tails, and they are the signature of a cluster's slow death. The process is a relentless gravitational tug-of-war. As a globular cluster orbits the galaxy, it does not travel through empty space. It moves through the Milky Way's diffuse but powerful gravitational field. The side of the cluster closer to the galactic center feels a stronger pull than the side farther away. This difference in force, the tidal force, stretches the cluster. Over billions of orbits, this constant stretching acts like a cosmic tide, pulling the most loosely bound stars, those on the outer edges, away from the main body. These escaped stars do not just vanish, they are shepherded by gravity into two long, streaming arcs, one leading ahead of the cluster in its orbit and one trailing behind. To visualize it, picture a globular cluster not as a perfect sphere, but as a dandelion head caught in a gentle but persistent breeze, its seeds being carried away in two opposite streams. These tidal tails are incredibly faint, often lost in the sea of background stars, but with powerful telescopes and sophisticated star-counting techniques, astronomers can now map them. And in mapping them, they gain something extraordinary, a direct readout of the galaxy's invisible gravitational skeleton. The stars in these streams all move together, tracing the precise path of the cluster's orbit through the galactic gravitational well. By studying the shape and density of a tidal tail, scientists can reverse engineer the distribution of dark matter in the Milky Way's halo, weighing our galaxy in a way no single instrument ever could. But these beautiful streams also tell a somber story. They are a forecast of the cluster's ultimate fate. With each passing orbit, more stars are stripped away. Given enough time, measured in hundreds of billions of years, the entire cluster will be dissolved into these long, thin rivers, its stars scattered and assimilated into the general population of the galactic halo. The tidal tails are both a birth certificate, mapping the cluster's long journey, and a death sentence written in starlight across the sky. The slow dissolution of a cluster by galactic tides hints at the immense forces at play in its core, where gravity's grip is absolute. This brings us to a hunt for one of astronomy's most elusive predators, the intermediate mass black hole. For decades, black holes seem to come in only two sizes: stellar mass, the corpses of giant stars, and supermassive, the monsters anchoring galaxies. But a middle child was missing, with masses hundreds or thousands of times that of our Sun. The dense cores of globular clusters became the prime hunting ground. The evidence is circumstantial but compelling, like finding claw marks around a hidden den. In clusters like Omega Centauri and G1, astronomers have observed stars near the core whipping around at unbelievable speeds. These velocities are too high to be explained by the combined gravity of all the visible stars packed into that central region. It is as if the stars are orbiting an invisible, incredibly dense anchor, an object with the gravitational pull of hundreds of suns squeezed into a point smaller than a city. Supporting this, some clusters emit faint but persistent X-ray flares from their hearts. the telltale signature of gas being torn apart and heated to millions of degrees as it falls into a deep gravitational well. Finding one of these intermediate mass black holes would be a monumental discovery. It would provide the missing link in black hole evolution. How do the supermassive giants in galactic centers grow so large? One leading theory is that they start as these intermediate mass seeds in dense star clusters, which then merge and consume more material over cosmic time. A globular cluster could be the nursery, the birthplace of a future galactic monarch. Furthermore, its presence would solve a long-standing puzzle about cluster cores. Without a central anchor, the densest clusters should experience a phenomenon called core collapse, where stars interact so violently they either merge or get flung out, leaving a dark, empty center. Yet many old clusters have stable, bright cores. An intermediate mass black hole could be the stabilizing force, the gravitational pivot that keeps the stellar city from consuming itself. The hunt continues, a detective story written in the frantic orbits of ancient stars and the faint, hot glow of devoured gas, all pointing to a hidden giant sleeping in the oldest cities of the universe. The search for hidden giants leads us to a discovery that redefines the boundary between star cluster and galaxy. In the vast galactic hinterlands, astronomers found objects that at first glance looked like unusually large globular clusters. But a closer look revealed something far stranger. These are ultra-compact dwarf galaxies, stellar systems so dense and massive they force us to question our very definitions. Imagine a sphere of stars containing tens of millions of solar masses, rivaling the heft of a small galaxy, but packed into a space only a few hundred light-years across. That is 100 times more mass than the largest globular cluster, squeezed into a volume just a few times larger. The first of these objects, discovered in the Fornax galaxy cluster, was so extreme it was initially mistaken for a single foreground star. Its true nature only became clear when its light was spread into a spectrum, revealing not one star but the combined glow of millions. So what are they? The leading and most dramatic theory is that they are the surviving hearts of devoured galaxies. Picture a small dwarf galaxy orbiting a giant like our Milky Way. Over billions of years, the relentless gravitational tides of the larger galaxy strip away its outer layers of stars and dark matter, a process called tidal stripping. What remains is just the dense, bright core, a galactic nugget that has been brutally shaved down to its essence. This corpse of a galaxy, stripped of its identity, then masquerades as a mere star cluster. Supporting this grim origin story, some ultra-compact dwarfs have been found to harbor their own supermassive black holes, a hallmark of a true galactic center, not a simple star cluster. Others show complex internal structures and multiple generations of stars, another signature of a richer history. Their existence solves one mystery while creating another. It suggests that what we see in the cosmos is not always what it started as. Some of the glittering points we catalogue as star clusters in the halos of giant galaxies might actually be the ghostly remains of entire galaxies that were consumed and digested long ago. They are cosmic imposters, the last survivors of a galactic feast, hiding in plain sight among the ancient cities of stars. The galactic ghosts known as ultra-compact dwarfs reveal a brutal cosmic history, yet the story of planet formation is not confined to such violent ends. It begins in the gentle, open arms of a stellar nursery. While we have found thousands of planets orbiting isolated stars, their presence within the loose, young families known as open clusters presents a profound puzzle. Open clusters like the Hyades or the Beehive cluster, Precep, are stellar siblings, groups of a few hundred to a few thousand stars born together from the same giant molecular cloud. They are young, often only a few 100 million years old, and their stars are loosely bound, slowly drifting apart over time. This is the environment where most stars, including our own sun, are born. And within these bustling stellar nurseries, astronomers have made a remarkable discovery: planets. This is strange because the theoretical deck is stacked against them. In the crowded, chaotic environment of a young open cluster, gravitational havoc is the norm. As newborn stars jostle for position, their powerful gravitational fields can violently disrupt the delicate protoplanetary disks of dust and gas swirling around their neighbors. A close stellar flyby can fling a fledgling planet into a wildly eccentric orbit, send it crashing into its star, or eject it entirely into the cold darkness of interstellar space. Given this gravitational minefield, we would expect open clusters to be barren, planetary dead zones. Yet they are not. The discovery of hot Jupiters, massive gas giants orbiting incredibly close to their stars within clusters like the Hyades, forces a dramatic rethink. How did these planets survive their violent childhood? Their existence suggests two thrilling possibilities. First, planet formation might be an incredibly rapid and robust process. The cores of giant planets could coalesce and accrete their gaseous envelopes with startling speed within the first few million years of the star's life, before the most disruptive gravitational encounters occur. They build their fortress of mass quickly, making them harder to dislodge. Second, and more intriguingly, these discoveries hint that gravitational chaos might not just destroy planetary systems, it might also forge them. A close stellar encounter could radically reshape a planetary system, scattering worlds into new, unexpected orbits, including the searingly close paths we see in hot Jupiters. The planet we find today, then, might not be in its birthplace, but in a new home carved out by celestial violence. Finding planets in open clusters does more than add to a catalogue. It provides a critical test of our planet formation theories in a realistic, dynamic environment. It tells us that planet building is not a delicate art requiring perfect solitude, but a hardy, resilient process that can withstand the rough and tumble of a star's earliest, most chaotic days in its stellar neighborhood. If planets can thrive here in the bustling galactic suburbs, then their potential for existence across the cosmos grows exponentially. The resilience of planets in open clusters shows how star formation can thrive in chaos, but at the very heart of some galaxies, this process has been permanently silenced. In the dense, bright centers of many galaxies, including our own Milky Way, sits a special kind of star cluster, a nuclear star cluster. These are among the most massive and dense stellar systems in the universe, packing millions of stars into a region just a few dozen light-years across. But in a significant number of galaxies, these central clusters present a profound mystery: they are quenched. This means they have completely and mysteriously stopped forming new stars, often for billions of years. Imagine the bustling core of a galactic capital, once a frenetic stellar factory, now frozen in time. Its population of stars aging uniformly with no young blue stars to break the monotony of ancient red light. The question is stark: what force is powerful enough to turn off star formation in the most resource-rich neighborhood in an entire galaxy? Astronomers point to two cosmic culprits, both tied to the monstrous supermassive black hole that also resides in that same central region. The first is called a GN feedback. An active galactic nucleus occurs when the central black hole is actively feeding on surrounding gas. This process does not happen quietly. It unleashes unimaginable torrents of energy in the form of intense radiation and powerful jets of particles that scream outward at nearly the speed of light. This energy blast can heat the surrounding gas to such extreme temperatures that it cannot cool down and collapse to form new stars. It is like a cosmic hurricane that permanently evaporates the rain clouds before a single drop can fall. The second possibility is more direct. The black hole, or the violent dynamics of the cluster itself, may have simply used up or expelled all the available cold gas, the raw fuel for star birth. Without a fresh supply, the cluster's stellar production line grinds to a permanent halt. These quenched nuclear clusters are not just curiosities, they are vital fossil records. Their state tells us about the violent history of their host galaxy. A quenched cluster signals a past era of ferocious black hole activity, a time when the galaxy's central engine was awake and reshaping its entire core. By studying the ages and compositions of the stars in these silent clusters, we can date that last burst of activity, piecing together a timeline of when the galaxy's central heart transitioned from a turbulent, star-forming youth to a quiet, aging maturity. They stand as enduring monuments to the most powerful forces in the cosmos, forces that can both create stellar cities and, with finality, turn out their lights for good. The silence of those ancient, quenched cores stands in stark contrast to a recent, deafening signal from a stellar nursery. In the year 2020, a wave of intense energy swept through our solar system, a burst of radio waves so powerful it temporarily blinded our radio telescopes and even disturbed Earth's upper atmosphere. Tracing this cosmic shout back to its source led astronomers to a surprising place, not an ancient relic, but a young, massive star cluster in our own galactic backyard. This was the discovery of a magnetar, a neutron star with a magnetic field so strong it defies earthly comprehension. This particular magnetar, named SGRJ 1935+2154, was found to be a member of the massive young cluster Westerlund 1. The association is what makes it extraordinary. Westerlund 1 is a stellar metropolis only about 5 million years old, filled with brilliant, massive stars still in the prime of their lives. To find the hyper-dense, dead corpse of a star among such vibrant youth is like finding a freshly dug grave in a playground. It tells a story of incredible violence and haste. The magnetar is the remnant of a star that was born, lived, and died cataclysmically within that short 5 million year window. The progenitor star must have been a true behemoth, perhaps 40 times the mass of our Sun. Such a titan burns through its nuclear fuel at a furious pace, living a life measured in mere millions of years before its core collapses in a supernova of unimaginable ferocity. In that final instant, as the star's core is crushed into a sphere the size of a city, its already powerful magnetic field is concentrated and amplified to insane levels. The result is a magnetar, a neutron star whose magnetic field is a quadrillion times stronger than Earth's. This force is so intense it can literally twist the star's solid crust, causing starquakes that release those titanic bursts of energy we detected. The presence of this magnetar in Westerlund 1 forces a profound realization. It means that within these young, glittering cities of stars, the most extreme and volatile objects in the universe are being manufactured right now. The cluster is not just a nursery for suns, but a factory for cosmic monsters. It shows us that stellar death is not a distant event relegated to ancient times, but an ongoing, violent process happening alongside stellar birth. A reminder that creation and destruction in the cosmos are two sides of the same brilliant, terrifying coin. That magnetar's violent birth cry is not the only echo from a stellar death. Sometimes the universe literally replays the final act. Around certain star clusters, astronomers have detected faint, expanding rings of light, ghostly reverberations from supernova that exploded centuries ago. These are light echoes, and they function as the cosmos's own delayed broadcast. The most famous example is not in a cluster but illustrates the principle perfectly, the remnant Cassiopeia A. When that star exploded roughly 350 years ago, its initial flash of light raced outward in all directions. Some of that light traveled directly to Earth, witnessed by astronomers in the late 17th century. But another portion of the light shot out in a different direction, striking a vast, distant cloud of interstellar dust. The dust absorbed that brilliant flash and then, slowly, re-emitted it, scattering the light toward us. Because this light took a longer, indirect path, it is only arriving at Earth now. We are not seeing the explosion itself, but its reflection, a luminous echo expanding across the sky over centuries. Now apply this to a star cluster. Imagine a supernova detonating within or near an ancient globular cluster millions of years ago. The direct light from that cataclysm faded into history long before human eyes looked up. But if that blast wave of light encountered a surrounding shell of dust, perhaps debris from earlier stellar winds, an echo could still be traveling. When we detect such an echo ringing a cluster today, we are granted a second chance to study that ancient explosion. We can analyze the echo's spectrum, breaking its light into a rainbow, to learn the exact chemical composition of the material ejected by the dying star. We can measure the echo's expansion rate to understand the violence of the blast. It is a cosmic time machine, allowing us to witness and dissect a singular event that should, by all rights, be lost to time. These faint, rippling halos transform clusters from simple collections of stars into historical archives with active playback. They prove that a star's death is not a momentary flash, but a story that can be told and retold across millennia, its final message inscribed on the dusty walls of space itself. These delayed broadcasts of stellar death are not the only way clusters preserve their history. They also lock secrets away in the very architecture of their stars. One of the most persistent and telling patterns astronomers find is an unusually high fraction of binary star systems. In some globular clusters, the number of stars that come in pairs is staggeringly high, far exceeding what we see in the general galactic field. This is not a minor detail, it is a fundamental feature that reshapes the entire life and destiny of a stellar city. Think of a binary system as a gravitational battery. Two stars locked in orbit possess a tremendous amount of kinetic energy in their motion around each other. In the crowded confines of a cluster, where stars are constantly brushing past one another, these binary systems act as the cluster's central energy exchange. When a single, wandering star passes too close to a binary, a complex three-body gravitational interaction occurs. The most common outcome is a gravitational slingshot. The single star gets a massive boost of speed and is ejected outward, often gaining enough velocity to escape the cluster entirely. In exchange, the binary pair loses some of its orbital energy, drawing the two stars closer together in a tighter, more intimate dance. This process is called hardening. This energetic trade has profound consequences. First, it acts as a cosmic pressure valve for the cluster's core. The intense gravitational energy that builds up as stars sink toward the center is siphoned off and converted into the kinetic energy that ejects stars. This prevents a catastrophic core collapse where all the stars would rush inward and merge in a chaotic frenzy. The binaries, by sacrificing their own orbital space, keep the stellar metropolis stable over billions of years. They are the shock absorbers of the system. Second, this high binary fraction directly challenges our most sophisticated computer simulations. Modeling the long-term evolution of a globular cluster is one of the most computationally intense tasks in astrophysics. Adding a significant population of binary stars increases the complexity exponentially. Every binary is not one object but two, with an intricate orbital dance that can be disrupted or altered by a passing star. Simulating the billions of years of gravitational ping-pong in a dense cluster with thousands of such systems pushes our most powerful supercomputers to their limits. When simulations without enough binaries run, they often predict clusters that evaporate or collapse faster than the ancient, stable ones we actually observe. The real universe, with its abundance of stellar pairs, is telling us that our digital models are missing a critical source of gravitational resilience. The prevalence of these binary systems forces a deeper question about their origin. Were they born this way, forming as paired stars from the same fragment of a collapsing cloud in the cluster's violent youth? Or were many of them created through capture, where two single stars brought together by the cluster's dense environment became gravitationally bound? The answer likely involves both, painting a picture of a dynamic environment where stellar partnerships are both a birthright and a product of circumstance. This high binary fraction is more than a statistic. It is the hidden infrastructure that maintains order in the cosmos's oldest cities, a delicate network of gravitational alliances that has ensured their survival across the lifetime of the universe. The gravitational slingshot that ejects stars is a gentle nudge compared to the violence that births a neutron star. Among the ancient stellar populations of globular clusters, astronomers have discovered the ultimate runaways, neutron stars rocketing through space at speeds exceeding 2 million miles per hour. These are not just escaping their birthplace, they are fleeing it with such ferocity they often leave a visible scar, a glowing trail of shocked interstellar gas in their wake. Their origin story is one of the most asymmetrical and violent events in the cosmos, a supernova with a deadly preference. When a massive star reaches the end of its life, its core collapses in a fraction of a second. If that collapse is perfectly spherical, the resulting neutron star would be born at rest, but nature abhors perfection. The prevailing theory is that the supernova explosion is profoundly lopsided. Instabilities in the collapsing core, perhaps driven by furious neutrino winds or powerful magnetic fields, act like a cosmic rocket engine. One side of the explosion is more powerful than the other, literally kicking the newborn neutron star like a football blasted from a cannon. This natal kick is unimaginably powerful, enough to overcome the gravitational pull of even a dense star cluster. The neutron star is shot out, carrying with it the directional memory of its mother star's final, unbalanced detonation. Finding these kicked neutron stars, often detected as lone pulsars far from any cluster's center, provides a critical forensic tool. By measuring their incredible speed and tracing their path backward, we can often pinpoint the exact region of a cluster where they were born millions of years ago. This allows astronomers to study the conditions that lead to such asymmetric explosions, but the story does not end with the kick itself. As these cosmic cannonballs barrel through the thin gas between stars, they act like supersonic boats plowing through a cosmic sea. The neutron star's powerful magnetic field and fierce particle wind slam into the interstellar medium, compressing and heating it. This creates a bow shock, a parabolic arc of glowing material ahead of the star, and often a long, faint tail of turbulent gas behind it. These trails are more than just pretty light shows, they are direct probes of the invisible environment. The shape and brightness of the bow shock tell us about the density and motion of the interstellar gas the cluster is moving through, material far too diffuse to see otherwise. Each of these speeding stellar corpses is therefore a double revelation, a messenger detailing both the violent mechanics of its own birth and the hidden landscape of the space it now travels. They are the ultimate testament to a truth written in momentum, that in the universe even death is not an end but a launch. The speed of a runaway neutron star is written in its momentum, but the composition of a star is written in its very atoms. This leads us to a chemical paradox buried within the oldest stellar cities. In the pristine, metal-poor environments of ancient globular clusters, astronomers have stumbled upon a class of stars that should not exist there, carbon stars. These are suns whose atmospheres are dramatically enriched with carbon, to the point that carbon molecules like C2 and Cn dominate their spectra, giving them a distinctive reddish hue. Their presence is a profound puzzle. You see, these clusters formed when the universe was young, from gas that had been seeded with only the lightest elements from the Big Bang, hydrogen and helium, plus trace amounts of lithium. Heavier elements, which astronomers collectively call metals like carbon, oxygen, and iron, did not yet exist in quantity. They are forged in the hearts of stars and scattered by supernova. So the first generation of stars in a globular cluster should be extremely metal-poor, and carbon is a metal in the astronomical sense. Finding stars rich in carbon in such an ancient, pristine environment is like finding a fully stocked modern kitchen in a prehistoric cave. It defies the standard narrative of chemical evolution. How did these stars get so carbon-rich without the usual cocktail of other heavy elements? the answer points to a peculiar and delicate form of stellar alchemy happening inside the stars themselves. In standard stellar evolution for low-mass stars, like those common in globular clusters, the final act involves the star becoming a red giant. During this phase, a process called dredge-up can occur, where convection currents from the deep interior bring nuclear fusion byproducts, including carbon, up to the star's visible surface. But in typical models, this process is not efficient enough to create the extreme carbon enrichment we observe in these cluster stars. Something else must be amplifying the effect. The leading theory involves a rare and finely tuned nuclear process happening in a shell around the star's inert helium core. In some stars, a thermal pulse, a brief but intense burst of helium fusion in a shell, can drive a particularly powerful convective dredge up. This event can pull large amounts of freshly made carbon from that shell and mix it into the star's outer layers. The star becomes a carbon star not because it was born from carbon-rich material, but because it manufactured the carbon internally and then wore it on its surface. But why does this happen so prominently in these specific metal-poor environments? The low initial metal content might actually be the key, with fewer heavy elements acting as catalysts for nuclear reactions or affecting the star's internal opacity. The internal dynamics of these ancient stars could be fundamentally different. The thermal pulses might be more violent or the dredge-up more efficient in this primordial chemical recipe. Each of these crimson stars is therefore a unique laboratory, a testament to a hidden branch of stellar evolution that only operates under the pristine conditions of the early universe. They force us to rewrite the cookbook for how stars process their internal elements, revealing that even in the simplest, oldest ingredients, nature can concoct surprising and complex results. The carbon stars demonstrate that a star's surface can lie about its origins, but sometimes the entire life cycle of a stellar population seems to blur before our eyes. In certain young to middle-aged star clusters, astronomers have noticed a strange smearing effect in their color and brightness diagrams. This is the extended main sequence turnoff phenomenon, and it presents a fundamental challenge to our most basic stellar timeline. In a simple, ideal cluster, every star is born at the same moment from the same cloud. They all begin their lives burning hydrogen in their cores, a stable phase called the main sequence. More massive stars burn hotter and brighter, living fast and dying young, while lower mass stars are frugal with their fuel, glowing dimly for trillions of years. On a graph plotting a star's color against its brightness, the main sequence appears as a crisp, clean line. The turn-off point is where this line curves. It marks the precise luminosity and color at which stars of a specific mass have finally exhausted the hydrogen in their cores and are beginning to leave the main sequence, ballooning into red giants. In a simple, single-age cluster, this turnoff should be a sharp, well-defined kink, but in many clusters it is not. Instead, the turnoff region is broadened, smeared, or even split into multiple branches, as if the stars are all leaving the party at different times. How can stars born together age at such different rates? Several compelling theories are rewriting our understanding of stellar youth. The first involves stellar spin. Stars can rotate at wildly different speeds. A rapidly spinning star experiences internal mixing, like a giant blender churning its interior. This mixing brings fresh hydrogen from the outer layers down into the core, effectively refueling the central furnace. A fast spinner can therefore stay on the main sequence longer than its identical, slow-spinning sibling, appearing younger in the diagram. The second theory posits a genuine, though small, age spread. Perhaps the cluster did not form in a single, instantaneous burst, but over a protracted period of 10 to 100 million years. In this scenario, the slightly older stars have already begun to turn off, while the slightly younger ones are still firmly on the main sequence, creating a blurred transition zone. The third major player brings back the gravitational complexities of binary stars. If a star is in a tight binary system, it can transfer mass with its companion. Gaining fresh hydrogen fuel can extend a star's stay on the main sequence, while losing mass can alter its color and brightness in complex ways, scattering stars around the expected turn-off point. This single, blurry feature in our data is therefore a crossroads of astrophysics. It forces us to acknowledge that a star's life story is not written by its birth mass alone, but is a narrative shaped by its rotation, its relationships, and even the precise timing of its ignition within the stellar nursery. The extended turnoff is not an error in our observations. It is the universe showing us the beautiful, complicated truth that even stars born as twins can live entirely different lives. The blurred aging of stars within a cluster hints at hidden, violent engines, and we have seen the direct proof. From the hearts of several ancient globular clusters, a faint but persistent glow of the universe's most energetic light bathes the cosmos in invisible fury. NASA's Fermi Gamma-Ray Space Telescope has mapped this diffuse gamma-ray emission emanating from multiple clusters, revealing a sustained torrent of energy that defies simple explanation. These are not the brief, brilliant flashes of gamma-ray bursts, but a steady, seething hum. The energy involved is staggering. Each photon of gamma-ray light carries billions of times more energy than a photon of visible light. To produce such a constant, high-energy output requires a relentless, powerful particle accelerator operating within the cluster itself. The prime suspect is a population of rapidly spinning neutron stars, the pulsars we have already met. These cosmic dynamos, with their immense magnetic fields, act as natural particle accelerators of unbelievable power. They can fling electrons and protons to velocities approaching the speed of light, creating a storm of ultra-relativistic cosmic rays within the cluster's confines. But a beam of particles alone does not make gamma rays. You need a collision. Here, the unique environment of the globular cluster provides the perfect target. The first target is light itself. Those accelerated particles moving at near light speed can slam directly into the relatively serene photons of starlight that fill the cluster. In a process known as inverse Compton scattering, the low-energy starlight photon gets a catastrophic boost from the high-speed particle, its energy rocketing up into the gamma-ray regime. It is as if a pebble thrown from a starship moving at light speed is transformed into a cannonball. The second potential target is the sparse, thin gas that drifts between the cluster's stars. When a cosmic ray proton smashes into a proton within this gas, the collision can produce a shower of secondary particles, including neutral pions, which almost instantly decay into pairs of gamma-ray photons. This creates a diffuse, all-encompassing glow that permeates the entire cluster volume. What makes this discovery so critical is that it reveals globular clusters as integrated high-energy physics labs. They are not just collections of stars, they are ecosystems where different forms of energy, kinetic, magnetic, and radiative, are constantly converted and recycled on a galactic scale. The steady gamma-ray glow is the signature of that conversion process, a beacon announcing that within these ancient cities, the machinery of particle acceleration is always running, forever weaving the fabric of light into its most extreme and potent form. Gamma rays are the signature of violence happening now, but the very existence of some clusters is evidence of a far older, slower kind of consumption. Scattered across the Milky Way's halo are stellar families with a secret past. They are not native to our galaxy. These are the lost sibling clusters, refugees from a series of ancient galactic cannibals. Their story is written in two languages, chemistry and motion. First, their chemical fingerprints are foreign. When astronomers analyze the light from these clusters, they find elemental ratios that are distinctly different from the majority of clusters that formed within the Milky Way itself. The amounts of iron, oxygen, and alpha elements like magnesium and silicon tell a tale of a separate star formation history. It is as if you compared the local dialect of a city to the accent of someone from a distant country. The foundational patterns are recognizably stellar, but the specific nuances are alien. Second, and perhaps more damning, are their orbits. These clusters do not travel on neat, circular paths within the Milky Way's disk. Instead, they move on highly eccentric, often plunging orbits that take them far out into the galactic halo and then back through the disk at steep angles. These are not the orbits of objects that formed in a settled, rotating galaxy like our own. They are the trajectories of captured objects, of survivors from a shattered system. The most famous example is the collection of clusters linked to the Sagittarius dwarf spheroidal galaxy. This small galaxy is currently in the process of being torn apart and devoured by the Milky Way's gravity. As it spirals in, its own globular clusters are being stripped away and donated to our galaxy's halo. Clusters like M54 are now considered the former nuclear star cluster of the Sagittarius dwarf, its very heart now beating in the chest of a giant. But the Sagittarius streams are just the latest meal. Other groups of clusters with similar strange chemistries and wild orbits are thought to be the remains of even earlier mergers, events so ancient that the dwarf galaxy they came from has been completely dissolved, its stars scattered beyond recognition. Only its toughest, most tightly bound globular clusters remain as identifiable tombstones. This means the serene halo of our Milky Way is not a quiet frontier, it is a cosmic graveyard and trophy room. Each of these lost sibling clusters is a captured relic, a piece of evidence in a multi-billion-year-old crime scene of galactic cannibalism. By studying their orbits, we can rewind the celestial clock and reconstruct the rough size and approach angle of the devoured galaxy. By studying their chemistry, we can read the star formation history of that lost galaxy, a history that ended when it was consumed by our own. They are more than just clusters, they are the last witnesses to the hierarchical growth of galaxies, proving that our majestic spiral was built piece by piece from the remains of its smaller neighbors. Those captured clusters are galactic fossils, but the largest of them all hides a secret in its frantic heart. Omega Centauri is a cosmic anomaly, a behemoth that outshines and outmasses every other globular cluster in the Milky Way by a staggering margin. It contains roughly 10 million stars, and at its core, those stars are not moving in a serene, orderly dance. Instead, they are spinning, and not all at the same speed. Astronomers have mapped the complex motions within this giant's core, discovering a layered rotation profile. Stars closer to the center whirl around the cluster's axis at a different rate than stars just a bit farther out. This differential rotation is a crucial clue, a fingerprint left by a violent past. In a typical, simple globular cluster that formed from a single cloud, you would expect the stars to move on random, elliptical orbits with little organized spin. They would buzz around like a swarm of bees, but the core of Omega Centauri rotates more like a miniature galaxy, with a distinct sense of a central axis around which everything turns. This kind of ordered motion is a hallmark of a system that had time to settle, to dynamically relax under its own immense gravity. It is exactly what you would expect from the dense central bulge of a dwarf galaxy. The leading theory, supported by its foreign chemistry and immense mass, is that Omega Centauri is not a true globular cluster at all. It is the stripped core of a dwarf galaxy that ventured too close to the Milky Way eons ago. Our galaxy's tidal forces ripped away the dwarf's outer stars and dark matter halo, leaving only this incredibly dense, bright nucleus behind. The complex rotation we see today is the lasting imprint of that galaxy's original spin, a ghostly memory of its former grandeur preserved in the motions of its surviving stars. This rotation also acts as a powerful stabilizing force, helping to explain why such a massive, dense object has not collapsed in on itself. The ordered motion provides a kind of centrifugal support, pushing outward against the inward crush of gravity, maintaining the core's structure over billions of years. So when we look at Omega Centauri, we are not just looking at a big star cluster. We are looking directly into the spinning heart of a devoured galaxy, a celestial engine still turning with the momentum of a lost world. The frantic spin of Omega Centauri's core speaks of galactic violence, but within the quiet suburbs of many clusters, a far more personal transformation is underway. Among the ancient red giants, astronomers occasionally spot a star of a different color, a pale, luminous yellow. These are not main sequence stars like our Sun, but rare and fleeting cosmic waypoints known as post-asymptotic giant branch stars. They represent one of the most ephemeral and critical phases in a star's life, a brief stopover between two giants. The journey to this point is dramatic. A Sun-like star exhausts the hydrogen in its core, swells into a red giant, and then, after a period of instability, enters the asymptotic giant branch phase. Here, it becomes a pulsating, luminous monster, shedding its outer layers in a series of powerful stellar winds. This is the star's final act of mass loss, a cosmic exhale that will determine its ultimate fate. When this shedding is nearly complete, something remarkable happens. The star, having ejected perhaps half its mass, suddenly contracts. Its outer layers collapse inward, and its exposed core, now fiercely hot, begins to heat the remaining thin shroud of gas. The star's surface temperature skyrockets from a cool red to a searing yellow or even blue-white, while its luminosity remains incredibly high. This is the post-asymptotic giant branch phase. The star is caught in a perfect, fleeting balance, no longer a swollen giant, but not yet a cooling, dense white dwarf. It is a star in rapid transition, and it only lasts for a few tens of thousands of years, a blink in cosmic time. Finding these yellow travelers in globular clusters is like finding a single frame from a fast-forward video of stellar death. Because all the stars in a cluster are roughly the same age, spotting a post-asymptotic giant branch star tells us the exact mass of star that is currently undergoing this final transformation. It acts as a precise clock, marking the moment when stars of that specific mass are leaving the giant branch forever. By studying their light, we can analyze the composition and speed of those final, powerful stellar winds, understanding exactly how much material a star returns to the cosmos before it dies. Each one is a crucial snapshot, a fossilized moment of metamorphosis that helps us complete the picture of how ordinary stars prepare for their silent, dense afterlife as white dwarfs. The brilliant, solitary yellow stars are brief cosmic waypoints, but within the same dense neighborhoods, far more predatory partnerships thrive. Some globular clusters are not just rich in stars, they are infested with X-ray binaries. These are not ordinary star systems, but duos locked in a deadly embrace, where a neutron star or a stellar mass black hole is actively siphoning material from a captive companion star. The stolen gas spirals inward at incredible speed, heating to millions of degrees and unleashing a torrent of high-energy X-rays. While a few such systems exist throughout the galaxy, certain clusters contain a shocking overabundance of them, far more than their stellar population should naturally produce. This is not a random distribution, it is a direct consequence of the cluster's extreme environment. In the serene emptiness between most stars, the formation of an X-ray binary is a rare and delicate process. It typically requires a binary star system where one massive member explodes as a supernova without completely destroying the partnership or kicking the remnant away. The odds are astronomically low, but in the crowded core of a globular cluster, the rules of engagement are rewritten by sheer gravitational traffic. Here, stellar encounters are not rare accidents, they are a fundamental part of the ecosystem. A lone neutron star, the remnant of an ancient supernova, can wander through the stellar city. If it passes close enough to a normal binary star system, a complex gravitational dance can unfold. The most likely outcome is an exchange encounter, where the neutron star swaps places with one of the original stars, effectively hijacking the binary system for itself. In an instant, a new X-ray binary is created not by birth but by capture. This process is so efficient in dense clusters that it can mass-produce these luminous predators. The cluster acts as a stellar matchmaking service, but one specializing in forced, violent partnerships. The overabundance of X-ray binaries is therefore a direct measure of the cluster's dynamic past. A cluster teeming with these X-ray sources is telling us it has experienced a frenetic history of gravitational interactions in its core. Each binary is a fossilized record of a close encounter that happened millions of years ago, a permanent partnership forged from a moment of cosmic chaos. They shine as beacons not just of accretion physics, but of the relentless social dynamics that define life in a city of stars. Those X-ray binaries are forced partnerships born from gravitational chaos, but near the very heart of our galaxy, we find unions of an even stranger kind. Orbiting the supermassive black hole at the Milky Way's core are bizarre entities known simply as G objects. They look like faint, puffy clouds of gas, but they move like massive, compact stars. This contradictory behavior makes them one of the most perplexing discoveries in modern astronomy. Imagine a cosmic shapeshifter, something that can stretch and distort like a wisp of smoke, yet possesses the gravitational heft and orbital stability of a sun. That is the essence of a G object. For years, they were dismissed as simple gas clouds until their orbits revealed the truth. They are traveling on coherent, elliptical paths around Sagittarius, a star, our galaxy's central black hole, completing loops that take hundreds of years. A loose cloud of gas would be torn apart instantly by the black hole's immense tidal forces, yet these objects hold together. So what are they? The leading theory is as dramatic as it is elegant. G objects are likely the products of stellar mergers, the hidden offspring of a dense nuclear star cluster that once swarmed the galactic center. In that incredibly crowded and violent environment, binary star systems could be driven to merge through gravitational interactions, either with the black hole itself or with other stars. When two stars spiral together and coalesce, they create a single, more massive star shrouded in a vast envelope of gas and dust, the stellar equivalent of a cocoon. This thick shroud gives the object its extended, cloudy appearance in infrared telescopes, hiding the brilliant star within, but gravity does not lie. The combined mass of the merged stars dictates its orbit, which is why it moves with the precision of a single, heavy body. These objects are living in a state of prolonged trauma. As they swing on their elongated orbits, diving perilously close to the black hole at periaps, the tidal forces stretch and distort their outer gaseous envelopes, pulling material away in long streamers. This process makes them appear to brighten and change shape periodically, like a comet being evaporated by the sun, but on a stellar scale. Their existence provides a crucial link to the past. They are likely the visible remnants of a once far more populous nuclear cluster, a dense family of stars whose members frequently collided and merged in the shadow of the monster they orbited. Each G object is therefore a fossil of a violent marriage, a testament to the extreme social dynamics that occur when countless stars are packed into the gravitational throat of a supermassive black hole. They are the universe's way of showing that even in the most hostile neighborhood imaginable, stars can find a way to unite, creating hybrid beings that defy all simple classification. These galactic mergers and violent unions rewrite a galaxy's history in bursts of fire, leaving behind a distinct chronological fingerprint in its star clusters. Astronomers examining the family albums of certain galaxies have stumbled upon a strange demographic pattern, a profound silence in the stellar record. The globular clusters in these galaxies do not show a smooth, continuous range of ages. Instead, they cluster into two distinct groups with a vast, empty chasm between them. There is an ancient population over 10 billion years old and a much younger population, perhaps only 2 or 3 billion years old. Between them lies a cosmic gap of 1 billion years or more, an era when it appears the galaxy completely stopped making new globular clusters. This is the age gap, and it signals a dramatic, system-wide hibernation followed by a violent reawakening. What cosmic event is powerful enough to shut down an entire galaxy's ability to form these massive stellar cities for such an immense span of time, and then restart the process? The leading suspect is a period of quenching, a cosmic drought induced by the galaxy's own central engine. In the early, gas-rich universe, a galaxy would form its first generation of globular clusters in a frenzied burst. But if that galaxy harbored a supermassive black hole that became active, the resulting torrent of energy from the active galactic nucleus could have sterilized the entire system. The fierce radiation and jets would heat or blow away the vast reservoirs of cold, dense gas required to form new clusters. The galaxy would enter a long, quiet era, its star formation effectively strangled. The billion-year gap represents this sustained period of inactivity, but then something reignited the furnace. The most likely catalyst is a major galactic merger. When another gas-rich galaxy finally collided with the quenched one, it delivered a colossal new fuel supply. This catastrophic event would have funneled enormous amounts of cold gas toward the center, triggering a second, spectacular epoch of cluster formation. The newborn clusters from this later era would bear the chemical signature of the merged galaxy's gas, distinct from the primordial clusters. This age gap is therefore a fossilized timeline of catastrophe and rebirth. It tells us the galaxy experienced two distinct lives, a violent youth, a long, quiet middle age imposed by its own black hole, and a dramatic renaissance born from a collision. The clusters are not just stars, they are chapters in a biography, with the empty space between them marking the most transformative event of all. A billion-year pause when the galaxy held its breath, waiting for a cosmic collision to write its next chapter. That billion-year pause in a galaxy's history is written in starlight, but a far more elemental mystery is etched into the atoms of the stars themselves. Within the atmospheres of the oldest stars in globular clusters, astronomers find a troubling absence, a missing ingredient from the primordial recipe of the cosmos. The element is lithium, and its scarcity presents one of the most persistent puzzles in all of cosmology, the lithium problem. According to our best models of the Big Bang, the first 3 minutes of universal creation should have forged precise amounts of the lightest elements, hydrogen, helium, and lithium. We can calculate with stunning accuracy how much primordial lithium should have been woven into the fabric of the first stars. Yet when we look at the ancient suns in globular clusters, which formed from that pristine early gas, their atmospheres show only about 1/3 of the predicted lithium. It is as if the universe carefully prepared a meal, set the table, and then someone removed 1/3 of the salt before anyone took a bite. This discrepancy is not a small error. It is a glaring hole in our understanding of either stellar interiors or the physics of the infant universe. The stars themselves are the prime suspects. Lithium is a fragile atom. At the relatively cool temperatures of a star's outer atmosphere, it is stable. But if that surface material is ever dragged down into the hotter interior, where temperatures exceed 2.5 million degrees, lithium nuclei are destroyed, fused into heavier elements like helium. The observed depletion suggests these ancient stars are far better mixers than we ever thought. Deep, slow-burning currents within the star, processes we call atomic diffusion or rotational mixing, could be constantly churning the stellar material, pulling lithium-rich surface layers down into the furnace to be burned away over billions of years. This would mean our standard picture of a star's interior, with neat, separate layers like an onion, is too simple for these ancient suns. Their hearts may be more like a slowly simmering pot, with subtle currents that gradually erase the lithium signature of their birth. But the other possibility is even more profound. What if the Big Bang calculations are wrong, not in a major way, but in some subtle detail of nuclear physics during those first fiery minutes? Perhaps an unknown particle interacted with the primordial soup, or a resonance in the nuclear reaction rates was slightly off, leading to less lithium production than our models predict. The ancient stars in globular clusters act as cosmic archaeologists, preserving a sample of that early material in their outer layers. Their severe lithium deficiency is a direct message from the dawn of time, a message we are still struggling to decode. Each measurement from these stellar fossils forces us to question our most fundamental stories, asking whether the flaw is in the stars that remember the past or in our theory of the past itself. The lithium problem is a quiet whisper from the dawn of time, but from the depths of space comes a shout so loud it defies all expectation. In recent years, a series of brilliant millisecond flashes of radio energy have been captured from galaxies billions of light years away. These are fast radio bursts, and their origin is one of the greatest mysteries in modern astronomy. Among these, one repeating burst in particular has sent a shockwave through the astrophysics community, for its traced location points not to a random patch of sky, but directly toward a distant globular cluster in another galaxy. This potential link, if confirmed, would be revolutionary. Fast radio bursts release more energy in 1,000th of a second than our Sun does in an entire day. To find such an extreme phenomenon associated with a globular cluster, a structure we have long considered ancient and relatively serene, would force us to completely reimagine the violent potential locked within these stellar cities. The prime suspect, should this connection hold, is a magnetar, the same type of star we met earlier as the source of gamma rays. But this would be a magnetar in an unimaginably extreme state, perhaps undergoing a starquake so catastrophic it cracks its own crust, releasing a titanic surge of energy into its powerful magnetic field. The dense environment of a globular cluster could be the perfect crucible for creating such a monster. The constant gravitational interactions could funnel material onto a neutron star, spinning it up to incredible speeds and amplifying its magnetic field to breaking point. Or a recent stellar collision or merger within the cluster could have freshly created a hypermagnetized neutron star in a volatile, unstable condition. If true, this means globular clusters are not just factories for magnetars, but for the most violently explosive magnetars in the universe, capable of broadcasting their agony across cosmic distances. This single, repeating flash from deep space challenges our entire classification of these ancient assemblies. It suggests that within their ancient cores, alongside the quiet red giants and serene binaries, lurk sleeping dragons capable of awakening with a roar that shakes the fabric of space-time itself. The perfect sphere is a cosmic ideal, but reality paints a different picture. Many of the ancient globular clusters we observe are not symmetrical balls of stars at all. Instead, they are subtly flattened, like a sphere gently pressed between two hands, or distinctly elongated, stretching into oval shapes across the sky. This asymmetry is not a flaw, but a profound clue written in the very architecture of these stellar cities. The shape tells a story of forces acting upon the cluster from within and without. The most common cause of flattening is rotation. Just as a spinning ball of pizza dough flattens into a disk, a cluster with even a modest amount of organized spin will bulge at its equator and compress at its poles. The stars within are not just buzzing randomly, they share a common direction of motion around a central axis, and that collective momentum sculpts the cluster's form. We see this in clusters like Omega Centauri, where the core's differential rotation imprints a distinct flattening on its overall structure, but rotation is not the only sculptor. The relentless gravitational pull of the Milky Way itself acts as a cosmic tide. As a cluster orbits the galaxy, the side closer to the galactic center feels a stronger tug than the far side. This tidal force constantly stretches the cluster along the line pointing toward the galaxy's heart, creating a permanent, slight elongation. It is a gentle but persistent pull, like the moon's grip on Earth's oceans, but acting on a scale of light years. In some cases, the asymmetry is a birth defect. A cluster may have formed from a collapsing cloud that was itself irregular or from the merger of two smaller stellar groups, leaving a lasting, lopsided imprint. These misshapen clusters are therefore dynamic fossils. By measuring their precise ellipticity, astronomers can estimate their internal rotation speed without needing to track every individual star's motion. They can gauge the strength of the galactic tides at the cluster's current location. A severely elongated shape might even hint at a recent, close encounter with a massive object like a giant molecular cloud or the galactic core, a gravitational shock that left the cluster permanently distorted. The perfect sphere is a textbook simplification, but the universe prefers character. Each flattened or stretched cluster is a unique record of its life story, a testament to the spinning, stretching, and shaking forces that have shaped it over billions of years. These brilliant, misshapen clusters are monuments to force, but the final breath of their stars can be sculpted into forms of shocking grandeur. Within the energetic confines of young, massive star clusters, astronomers have found planetary nebulae of impossible scale, cosmic ghosts that dwarf any found in isolation. A planetary nebula is the final, beautiful sigh of a dying sun-like star, a luminous shroud of gas expelled during its death, throes and illuminated by the star's hot, exposed core. Normally, these glowing shells are a few tenths of a light year across. Yet in these specific clusters, they balloon to sizes exceeding a full light year, becoming superplanetary nebulae. Their inflated majesty is not a product of a more massive star, but of the star's violent neighborhood. The cluster environment itself is acting as a cosmic bellows, dramatically altering the death process. The key is the intense radiation field and the powerful stellar winds that flood a young cluster. When a star begins its final transformation, shedding its outer layers to form a nebula, it does so against a relentless headwind. In isolation, this stellar wind expands into a near vacuum, but inside a bustling young cluster, it pushes against the combined pressure of radiation and wind from thousands of brilliant, massive neighbors. This external pressure effectively squeezes the dying star's outflow, confining it and forcing it to accumulate into a denser, slower expanding shell. Think of it like blowing up a balloon inside a strong, steady breeze. The balloon inflates, but the wind presses against one side, shaping it and causing it to swell into a larger, more distorted form over time. Furthermore, the sheer density of stars increases the chance of gravitational interactions. A close pass from another cluster member could gravitationally strip material from the dying star in a more dramatic, one-time event, dumping a huge amount of gas into the surroundings at once. This ejected shell, now larger and more massive than usual, is then lit up by the central star's ultraviolet radiation, creating a beacon far brighter and more extended than its solitary cousins. These supernebulae are therefore not just larger ghosts, they are direct environmental products. Their grand scale is a fossilized record of the pressure and chaos their parent star endured in its final moments, a luminous testament to how a stellar city's collective energy can reshape the very process of death, turning a whisper into a shout that echoes across light years. The most beautiful destruction in our galaxy might belong to a cluster named Palomar 5. While all clusters face eventual dissolution, Palomar 5 is in the midst of a spectacularly slow-motion disintegration, and the motions of its stars are writing a unique story across the sky. This cluster is so thoroughly stretched that its most defining feature is not its core, but the immense, graceful tidal tails that stream from it for thousands of light years. Yet within this unraveling tapestry, the individual stars are not moving in a simple, predictable flow. Their precise paths, their kinematics, hold a faint but vital signal. By mapping the subtle twists and speeds within those long stellar streams, astronomers are hunting for the fingerprints of invisible sculptors. The primary suspect is not the smooth pull of the Milky Way's overall dark matter halo, but something more elusive: dark matter subhalos. These are predicted to be clumps of dark matter, the leftover building blocks from our galaxy's formation, still wandering the halo like invisible icebergs. As Palomar 5's stream of stars sweeps through the galaxy, a close pass by one of these dense, unseen subhalos would gravitationally pluck at the stream, creating a distinct kink or gap in the otherwise smooth ribbon of stars. It would be a cosmic interaction felt but not seen, a disturbance with no visible cause. The other potential sculptor is a known but powerful force, the central galactic bar. This dense structure of stars at the Milky Way's heart rotates, and its gravitational influence can create resonances, rhythmic tugs that can pinch or warp a stellar stream over time. Palomar 5, in its delicate, stretched state, is the perfect detector for these subtle forces. Its stars are like a billion grains of sand scattered along a shoreline. By studying exactly how their line is distorted, we can deduce the shape and strength of the tides and the hidden objects moving through the deep. The strange kinematics of this dying cluster are therefore a form of celestial cartography. They allow us to map the invisible substructure of our galaxy's dark matter in a way no telescope ever could, using the torn-apart remains of a stellar city as our guide. The violent mergers that create superplanetary nebulae are not the only way a star can be given a second life. Within the dense cores of these ancient cities, a star can cheat time itself through a catastrophic embrace. Astronomers find stars that burn with the fierce blue heat of youth, yet they dwell in neighborhoods over 10 billion years old. These are not the blue stragglers formed by slow theft of fuel, but something more dramatic, the products of direct stellar collisions. When two stars, driven together by the complex gravitational tides of the cluster core, slam into one another, they do not simply explode. Instead, they can merge into a single, more massive star, a stellar phoenix born from a fiery crash. This merger is a cosmic reset button. Imagine two aging, sun-like stars, each having exhausted the hydrogen in their core, well on their way to becoming red giants. Their interiors are layered with the ash of nuclear fusion, helium and heavier elements. When they collide and merge, the resulting star is not just the sum of their masses, its entire internal structure is violently scrambled. The fresh hydrogen from the outer layers of both stars gets mixed deep into the new, larger core. This sudden infusion of pristine fuel reignites hydrogen fusion at a ferocious rate. The star's outer layers heat up, its color shifts from a cool red or yellow to a brilliant blue-white, and it leaps backward on the evolutionary timeline. It is now a massive, hot star living a new life, but with the chemical memory of its two ancestors locked inside. This process of stellar rejuvenation solves a key mystery. It explains how we can see such brilliantly hot stars in places where all the original massive blue stars should have died eons ago. The cluster is not just preserving ancient stars, it is actively manufacturing new ones from old parts, a cosmic recycling program of the most violent kind. The clock for this new star starts ticking from zero, granting it a lifespan of millions rather than billions of years, a second chance written in fire and gravity. This means the population of a globular cluster is not a simple snapshot of a single birth event, but a living palimpsest where the stories of individual stars are constantly being erased and rewritten by the relentless traffic of the stellar city. That stellar phoenix born from a violent merger leaves a brilliant trail, but not every star in a cluster is destined for such a dramatic fate. Many face a quieter exile, and their collective sigh forms a ghostly background glow known as diffuse intracluster light. This is the faintest light in the universe, a soft, ethereal haze that permeates the space between the bright, concentrated stars of a cluster. It is not the glow of gas, but of billions of individual suns that have been gravitationally evicted from their home galaxies and now drift lost in the immense voids between them. To see it, astronomers must perform a kind of cosmic subtraction, meticulously removing the light from every identifiable galaxy and star, revealing the leftover, whispering luminescence that remains. This faint glow is the forensic evidence of a cluster's violent past. Every close encounter between galaxies, every tidal stripping event, every act of galactic cannibalism does not just move stars from one galaxy to another. It also flings a significant fraction of them out into the intergalactic void. These stars become orphans, no longer bound to any galaxy, but still trapped by the immense gravity of the cluster as a whole. They form a vast, diffuse cloud that can extend for millions of light years, far beyond the visible boundaries of the cluster's galaxies. This intracluster light is therefore a historical record. By mapping its distribution and brightness, astronomers can read the story of how the cluster assembled itself. A smooth, spherical halo of this light suggests an ancient, relaxed cluster where mergers happened long ago. A lumpy, asymmetrical glow, however, points to recent or ongoing violence, with stellar streams still visible as faint ripples in the ghostly sea, marking the paths of recently devoured galaxies. But this light is more than a history book, it is a scale. The total amount of intracluster light is directly linked to the total mass of the cluster, including the vast, invisible halo of dark matter that holds the entire structure together. The more massive the cluster's gravitational well, the more stars it can capture and hold in this diffuse state. By measuring the faint glow, scientists can effectively weigh the cluster's dark matter halo, using the lost stars as tracers of the deepest gravitational potentials. These wandering suns, forever separated from their galactic homes, thus perform a crucial final service. Their combined, feeble light illuminates the invisible architecture of the cosmos, mapping the dark scaffolding upon which the universe builds its greatest cities. These wandering stars map the dark, but the quiet dead among them hold a different kind of surprise. Within the ancient stellar populations of globular clusters, astronomers are finding white dwarfs that simply do not weigh enough. A white dwarf is the final, cooling ember of a star like our Sun, a sphere of degenerate matter where gravity is balanced by a quantum mechanical pressure. Physics dictates a strict rule for their creation. A star must shed its outer layers until only its dense core remains. That core has a predictable mass, typically around 55 to 60% of our Sun's mass. Yet in clusters, we find white dwarfs tipping the scales at only 20 or 30% of a solar mass. How can a star leave behind such a lightweight corpse? It suggests the star did not just shed its envelope, it was robbed of it long before its natural death. The leading explanation involves a partner and a theft. In a close binary system, a star beginning its expansion toward the red giant phase can have its outer hydrogen layers systematically stripped away by its companion. This could be a neutron star or another white dwarf, siphoning material so efficiently that the aging star is peeled down to its bare helium core long before it would have naturally exposed it. The result is a helium white dwarf, a low-mass remnant that skipped the final, dramatic act of its life. But there is another, more violent path. In the dense cluster core, a direct collision could tear the envelope clean off a red giant star. Imagine two stars grazing one another in a close gravitational encounter, a cosmic sideswipe that shears away the puffy, extended outer layers of one star like peeling a fruit, leaving the dense core exposed and unattached. This core, no longer able to sustain fusion, would then cool directly into a low-mass white dwarf. These underweight stellar ghosts are therefore forensic evidence. Each one is a signpost pointing to a dramatic past, a life cut short or radically altered by companionship or catastrophe. Their presence in numbers tells us that the quiet end we envision for our own sun, a gentle puffing away of its layers into a planetary nebula, is not the only destiny. In the crowded cities of stars, death often comes early and from the hands of a neighbor. Galactic collisions do not just destroy, they create on a scale that defies imagination. When two immense spiral galaxies like the antennae galaxies lock in a gravitational embrace, they do not simply pass through one another. Instead, their vast clouds of interstellar gas are compressed, shocked, and funneled into long, luminous arcs that stream away from the chaos. Within these tidal tails, astronomers witness a stellar miracle, the birth of entire generations of stars not as isolated suns, but as brilliant, dense clusters strung along the filament like pearls on a cosmic necklace. This is the string of pearls phenomenon, and it reveals that the most fertile nurseries in the universe are often born from the most violent events. The process begins with the raw material. As the galaxies interact, their mutual gravity pulls immense rivers of gas and dust out into space. These tidal tails are not smooth streams, they are turbulent and filled with knots and clumps where the density soars. In these dense pockets, gravity finally overcomes the pressure and heat of the collision, and the cloud begins to collapse. But here is the key difference from isolated star formation: the scale is monumental. The collapsing clouds are not forming single stars, they are massive enough to fragment into hundreds or thousands of stellar seeds at once. What emerges is not a loose association, but a bound young star cluster, blazing with the fierce blue light of newborn massive stars. Each bright knot along the tail is one of these clusters, a stellar city in its infancy. The antennae galaxies showcase this in stunning detail, with dozens of these superstar clusters, each containing millions of stars gleaming along its vast, sweeping arcs. These are not the ancient, stable globular clusters we find in our halo, but they're likely progenitors caught in the act of formation. This observation solves a long-standing mystery. It shows us where and how the universe builds its most massive stellar systems. The incredible forces of a galactic merger provide the perfect pressure cooker, concentrating enough material in one place to forge not just stars, but entire communities of stars destined to remain bound together for billions of years. It is a breathtaking cycle where the destruction of galactic order gives birth to a new, tighter order, a legacy of brilliant pearls cast into the darkness from the wreckage of giants. The brilliant pearls of new star clusters are forged in violence, but where are the echoes of the old explosions? Ancient globular clusters present us with a ghostly absence, a crime scene with no visible body. Within these cities of 10-billion-year-old stars, we find ample evidence of stellar death, neutron stars and white dwarfs, but we see almost none of the expected supernova remnants. These are the glowing, expanding shells of gas that should mark the spot where massive stars ended their lives in catastrophic explosions. Their near-total absence is a profound cosmic silence. If these clusters formed with massive stars, and we know they did from the chemical pollution in their surviving members, then those titans must have exploded. So where did all the wreckage go? The first possibility is one of sheer violence and speed. A supernova remnant in isolation, like the famous Crab Nebula, expands into a near-perfect vacuum. It can glow visibly for tens of thousands of years before fading, but the environment inside a globular cluster is anything but a vacuum. The space between stars, while vast, is filled with a tenuous but measurable amount of gas, the combined stellar winds of every red giant and hot star in the system. When a supernova blast wave erupts into this medium, it does not expand freely. It slams into this pre-existing wind, creating a shock that dissipates the remnant's energy much more rapidly. The furious expansion might be slowed and the glowing shell mixed and diluted into the general cluster haze within just a few thousand years, a blink in the cluster's long life, making it incredibly unlikely for us to catch one in its brief, visible phase. The second theory involves a different kind of death. Not all supernova leave behind a traditional expanding nebula. The most massive stars might collapse directly into black holes with a whimper rather than a traditional bang, a so-called failed supernova that ejects little visible debris. Alternatively, the supernova in these pristine, low-metal environments of the early universe might have been of a different type altogether, perhaps pair instability supernova that completely obliterate the star, leaving no dense core behind and creating a remnant that is more diffuse and quick to fade. The third and simplest explanation is time. These clusters are ancient. Any supernova remnant that did form would have been expanding for billions of years. Over such an immense timescale, even a slow-moving shell would have grown to a size of hundreds of light years, its material stretched so thin that its surface brightness has dropped below our ability to detect it. The remnant would have merged with the general interstellar medium of the galaxy long ago, its atoms recycled into later generations of stars elsewhere. This absence forces a shift in perspective. We must learn to read the evidence of stellar death not in glowing nebulae, but in the silent, compact objects left behind and the chemical fingerprints sprayed into the cluster's next generation of stars. The missing remnants are not an error in our theories, but a lesson in cosmic forensics, teaching us that the most violent chapters in a cluster's history are often written in invisible ink, faded with time, leaving only the durable bones of the dead as their testament. Buried within the quiet light of ancient clusters are stars that keep time on a scale we can barely comprehend. These are the ultra-long period variable stars, giants whose brightness does not flicker in days or months, but rises and falls in majestic cycles that can last for several years. Imagine a stellar heartbeat so slow that a single pulse from dim to bright and back again spans longer than a presidential term or the entire duration of a world war. This is not the rapid, chaotic twinkling of a star in its death throes, but a deep, resonant oscillation, a fundamental rhythm of the star's very structure. These stars are not main sequence suns like our own. They are evolved red giants or asymptotic giant branch stars, swollen to hundreds of times the diameter of our Sun. Their immense, tenuous outer layers are the key to the mystery. The driving force behind these long cycles is a delicate and ongoing battle deep within the star. In the shell of helium ash surrounding the star's inert core, nuclear fusion periodically ignites in a thermal pulse. This sudden burst of energy does not explode outward. Instead, it pushes against the overlying layers of hydrogen, causing the entire outer envelope of the star to slowly expand and cool. As it expands, it becomes more transparent, allowing more of the star's internal light to escape, and the star brightens in our sky. Then, over the course of years, gravity reasserts its control. The puffed-up envelope slowly settles back inward, compressing and heating, which paradoxically makes it more opaque. The star then dims as less light can fight its way out. This cycle of expansion from heat and contraction from gravity creates that incredibly slow, regular pulse. Discovering these stars in globular clusters is a gift to astrophysics because it gives us a direct probe into the hidden interiors of these elderly giants. By precisely measuring the period of the pulsation and the amount the star brightens and dims, astronomers can perform a kind of cosmic sonogram. The period of the oscillation is directly linked to the star's mean density. A slower beat means a larger, more diffuse star. The amplitude of the change, how much brighter it gets, tells us about the efficiency of the energy transfer through those outer layers. Each of these slow-beating giants is therefore a natural laboratory, its rhythmic breathing allowing us to map conditions in regions we could never otherwise see, revealing the timing of nuclear shell burning and the strength of gravitational settling in some of the universe's oldest, most bloated stars. Their patient light holds the tempo of a hidden, interior universe. The slow, rhythmic breathing of ancient giants reveals a stable interior, yet the very atoms that compose them tell a story of profound and early chaos. This brings us to a discovery that dismantles the simplest story of a cluster's birth. We must now look deeper into the chemical variation within a single cluster, the multiple population phenomenon. It is not merely that some stars are polluted and others are not. The differences are stark, systematic, and written in specific elements. Within the same ancient family, astronomers find stars with wildly different abundances of helium, nitrogen, sodium, and oxygen. One star might have normal amounts of oxygen and magnesium, while its neighbor, born from the same primordial cloud, is severely depleted in those elements but is instead enriched with 10 times more sodium and 100 times more nitrogen. Even more striking, some stars show a dramatic overabundance of helium, the second most common element in the universe. This is not a minor variation, it is a fundamental schism in the cluster's stellar DNA. The challenge this poses to the classic monolithic formation model is immense. That old model said a globular cluster formed in a single, rapid, isolated collapse of a giant molecular cloud. Every star in that cluster should be a chemical twin, sharing the identical elemental recipe of that parent cloud. The multiple populations are a direct and violent refutation of that idea. How can stars from the same birth cloud have such radically different chemistry? The answer forces us to envision the cluster's youth as a place of both creation and contamination. The leading theory, as we've touched on, involves a staggering two-act drama. The first generation of stars, the true primordial population, forms from the pristine gas. Among them are moderately massive stars, perhaps 8 to 10 times the mass of our Sun. These stars do not end in supernova, they live longer and die in a different way. In their advanced age, they become asymptotic giant branch stars, and during this phase, they eject their outer layers through powerful, slow stellar winds. This ejected material is not pristine. It has been processed through the star's interior nuclear furnaces. Deep inside, at incredible temperatures, the star fuses hydrogen into helium via the C&O cycle. This cycle not only produces helium, but it also converts carbon and oxygen into nitrogen. Simultaneously, a separate process called neon burning can produce sodium while depleting oxygen and magnesium. So the wind from this dying star is a toxic soup, rich in helium, nitrogen, and sodium, and poor in oxygen and magnesium. This polluted gas then mixes with whatever remains of the original, pristine hydrogen gas in the cluster's core. From this second-generation mixture, a new wave of stars is born. These stars carry the chemical signature of the first generation's death throes. They are the polluted population, the helium-rich, sodium-rich, nitrogen-rich stars we observe today. This scenario solves the chemical mystery, but it creates a staggering logistical problem. To produce the sheer number of second-generation stars we see, which often outnumber the first generation, the initial cluster must have been far more massive than it is today, perhaps 10 or 20 times heavier. It would have needed an immense reservoir of gas to form that first generation of polluters, and then to form the second generation from the polluted mix. Most of that original mass, the pristine gas and many of the first generation stars, must have been violently expelled from the cluster early on, leaving behind the chemically divided family we see today. This means the serene globular cluster is a survivor, the dense, resilient core of a system that was once a titanic stellar metropolis, its history of creation and loss forever inscribed in the contrasting light of its stars. Even the most massive stars can be cast out from their birthplace. In the heart of the Tarantula Nebula, a stellar factory of unimaginable violence, lies the dense cluster R136. It is a cauldron of newborn giants, home to the most colossal stars we know, some weighing over 200 times the mass of our Sun. Yet astronomers have spotted several of these stellar behemoths not at the cluster's brilliant core, but fleeing its edges at tremendous speeds. These are runaway massive stars, and their exile is a direct result of the gravitational pandemonium that defines their youth. How does a star containing the material of hundreds of suns get thrown out of its own home? The ejection mechanisms are as dramatic as the stars themselves. the most likely scenario is a gravitational slingshot involving a tight, massive binary system. In the dense core of R136, such a binary can wander too close to another massive star or even another binary. What follows is a chaotic gravitational dance. In this multi-star encounter, kinetic energy is traded like currency. One star, often the least massive in the interaction, can be flung outward at an astonishing velocity, sometimes exceeding 100 kilometers per second. It is a cosmic game of billiards played with stellar titans, where the cue ball is the gravity of a passing star and the prize is escape velocity. Another possibility is the explosive breakup of a multiple star system. If a tight trio or quartet of massive stars becomes dynamically unstable, their orbits can decay catastrophically. The system violently ejects one or more members to achieve a stable configuration, launching the outcasts on trajectories that carry them clear of the cluster's gravitational grip. These runaway giants do not travel quietly. As they plow through the surrounding nebula at breakneck speed, their fierce radiation and powerful stellar winds act like a cosmic plow. They compress the gas ahead of them, potentially triggering new, off-center star formation far from the main cluster. They also carve out vast cavities and sculpt the nebula itself, their brilliant, solitary light acting as a beacon that marks the path of their expulsion. The very existence of these runaway stars from R136 provides a crucial reality check for our models of extreme star formation. It proves that the cores of these superlative clusters are not just places of birth, but arenas of relentless dynamical violence, where even the heaviest and brightest residents are not immune to being evicted by the gravitational tides of their equally monstrous neighbors. The silent, rhythmic hum of the cosmos has finally been heard. Advanced observatories like LIGO and Virgo have detected not just individual collisions of black holes and neutron stars, but a persistent, low-frequency murmur underlying them all, a gravitational wave background. This is the collective vibration of spacetime itself, and a significant portion of this cosmic hum is now believed to originate from the ancient, crowded hearts of globular clusters. These stellar cities are predicted to be relentless factories for binary neutron star mergers, events of such unimaginable density and violence that they send ripples through the fabric of reality. To understand why, picture the environment. A globular cluster's core is a gravitational traffic jam of staggering proportions, with thousands of stars packed into a space just a few light-years across. In this chaos, neutron stars, the ultra-dense corpses of massive stars, are not rare, they are common, and in such a dense environment, these stellar corpses rarely stay lonely for long. Through a process of gravitational exchange, two neutron stars can find themselves locked in a tight, decaying orbit. They might be the survivors of two separate massive binary systems that interacted, or a single neutron star could have captured another through a close encounter, hijacking it as a partner. Once formed, this binary neutron star pair is a clockwork tragedy. As they spiral around each other, they radiate energy in the form of gravitational waves, those very ripples in space-time. This loss of energy causes their orbits to shrink, imperceptibly at first, but with increasing speed over hundreds of millions of years. Their final moments are a crescendo of orbital decay, culminating in a merger of incomprehensible force. Two city-sized objects, each containing more mass than our Sun, smash together at a significant fraction of the speed of light. The resulting kilonova explosion forges heavy elements like gold and platinum, but it also unleashes a thunderclap of gravitational waves, a sharp chirp that rises in frequency before cutting off. Now imagine not one, but thousands of these binary pairs, scattered across the countless globular clusters in the universe, all in various stages of this slow, inescapable dance. They do not merge in unison, but their individual chirps and rumbles, overlapping across billions of years and millions of light years, blend into a steady, statistical hum. This is the gravitational wave background contribution from clusters, a continuous whisper of space-time strain born from countless catastrophic unions in ancient stellar cities. This prediction transforms our view of these clusters once more. They are not just optical wonders or chemical fossils, they are active contributors to the universe's fundamental symphony. By studying the properties of this hum, its amplitude and frequency, astronomers can indirectly census the population of these tight binary neutron stars across cosmic time, objects that are otherwise nearly impossible to see. It suggests that the serene points of light in our telescope's eye are, in truth, ceaseless engines of space-time vibration, their most violent interactions written not in light, but in the subtle stretching of the universe itself. That gravitational hum of merging neutron stars speaks of a universe built on extremes. But what if the most delicate possibilities for life exist right beside them? Our journey through strange discoveries now takes us to the edge of speculation, to the hypothetical moons of planets that might orbit stars within these ancient clusters. If a planet can survive the gravitational chaos, could its moons harbor worlds of ice and fire? The concept is cryovolcanism, and it offers a stunning vision of alien geology. Imagine a moon not of rock but of solid ice wrapped around a dense, rocky core. This frozen world orbits not just its planet, but dances within the complex gravitational field of a tight binary star system, or feels the constant pull from nearby cluster neighbors. This relentless, varying gravitational flexing, known as tidal heating, generates immense internal friction. The moon's interior warms not from the distant sun's rays, but from this constant gravitational kneading. Deep beneath the icy crust, this heat can maintain a vast, global subsurface ocean of liquid water, sealed away from the cold vacuum of space, and when pressure builds, this ocean finds a way out. It erupts. Instead of molten rock, these volcanoes spew water, ammonia, methane, or other volatile compounds that freeze instantly in the vacuum, creating towering, glittering geysers and coating the landscape in exotic frozen slush. We see this happening in our own solar system on moons like Enceladus around Saturn and Europa around Jupiter. But within a star cluster, the tidal forces could be far more intense and complex, potentially creating even more dramatic and sustained cryovolcanic activity. This leads to the most profound speculation of all. That hidden, tidally heated ocean, protected by a thick shell of ice and kept liquid for billions of years by gravitational energy, could be a perfect crucible for chemistry. It would have heat, water, and likely organic molecules delivered by comet impacts long ago. In the most hostile stellar neighborhood imaginable, bathed in radiation and gravitational chaos, a warm, dark sea could persist. It is a staggering thought that the ancient cities of stars, forged in violence and home to stellar predators, might also cradle the most delicate possibility of all: hidden oceans on frozen moons, whispering of environments where life could, against all cosmic odds, begin. The silent, rhythmic hum of merging stars might be a universal soundtrack, but the paths they travel tell a more personal story of our galaxy's past. The ancient globular clusters orbiting the Milky Way do not wander aimlessly. For decades, we assumed their journeys were a random, swirling swarm, a legacy of chaotic mergers from all directions. But modern sky surveys reveal a startling pattern. The orbits of many clusters are aligned, as if they are marching to the beat of a long-forgotten drum. This is not a perfect, single-file line, but a distinct statistical preference. A significant number of these stellar cities share similar orbital planes, their paths tilted in a common direction relative to the disk of the Milky Way. This alignment is a fossilized imprint of a single, colossal meal our galaxy consumed in its distant past. Imagine our galaxy as a predator, and each globular cluster is a bone from its prey. If the galaxy ate many small snacks from random angles, the bones would be scattered in every direction. but if it devoured one enormous feast, the bones from that one victim would tend to point in a similar way. The aligned clusters are those bones. They are the surviving members of a dwarf galaxy that was torn apart and digested by the Milky Way, likely over 8 billion years ago. As that satellite galaxy was shredded, its own globular clusters were stripped away, but they retained the memory of their original motion, the shared orbital direction they had within their parent system. That collective momentum was imprinted on them, and even after billions of years of orbiting within our galaxy's vast halo, that alignment has not been completely erased by gravitational perturbations. It persists as a whisper of a lost structure. This discovery forces a profound shift in how we view our galaxy's growth. It suggests that a major portion of the Milky Way's halo, its outer skeletal structure, was built not from 100 tiny mergers but from one or two monumental ones. The aligned clusters are tracing the ghostly backbone of that devoured giant, a structure astronomers now call the Gaia Sausage or the Gaia Enceladus galaxy. This single, ancient collision did not just donate stars, it may have violently puffed up the Milky Way's own disk and fundamentally shaped its early architecture. By mapping the precise orbital poles of these aligned clusters, we are essentially doing galactic paleontology, reconstructing the size, approach angle, and even the spin of the galaxy that died to build our own. Their coordinated motion is a silent testimony to the hierarchical nature of the cosmos, where giants are built from the remains of other giants, but the implications reach even farther than our own galactic backyard. If such alignments are common in other galaxies, they could reveal a universal pattern in how cosmic structures assemble, a hidden order written in the synchronized dance of the oldest objects in the universe. The synchronized orbits of ancient clusters map a galaxy built from giants, but where do the clusters themselves come from? The answer might lie in a bizarre, modern class of cosmic objects so strange they were named by amateur astronomers. Scattered across the sky are tiny, brilliant galaxies glowing with an intense emerald green light. Catalogued by online volunteers as green peas, these galaxies are nothing like the majestic spirals we know. They are small, compact, and undergoing a frenzy of star formation so violent it defies belief. Within a volume not much larger than a globular cluster itself, a green pea galaxy can be forming stars hundreds of times faster than our entire Milky Way. This creates an environment of staggering pressure and density, a superheated cauldron where stars are not born in ones or twos but in vast, simultaneous bursts. The significance of these tiny green powerhouses is profound. They could be the missing link, the modern-day analogues of the conditions that forged globular clusters in the early universe. When we look at a green pea, we might be witnessing the birth of a future globular cluster in real time. The process is one of extreme compression. In the primordial universe, the first giant molecular clouds were likely denser, hotter, and more turbulent than those we see today. When such a cloud collapsed, it wouldn't form a single star or a loose association. It would fragment into thousands of stellar seeds at once, all bound together by their mutual gravity from the very beginning. A green pea galaxy seems to be doing exactly that, but in the modern cosmos. Its entire structure is essentially one gigantic, collapsing star-forming region. The ferocious radiation from its countless newborn massive stars floods the galaxy, but crucially, that radiation and the powerful supernova winds may be unable to blow away the remaining dense gas. Instead, the intense gravity of the burgeoning stellar swarm holds the gas in place, allowing star formation to continue in a runaway cascade until nearly all the fuel is converted into stars. What remains is a massive, tightly bound, spherical city of stars, all sharing the same age and chemistry, a newborn globular cluster. If this model holds, then green pea galaxies are not just curiosities, they are time machines. By studying their internal dynamics, their gas content, and the properties of their stellar populations, we can test our theories about the most intense mode of star formation possible. We can measure how efficiently gas turns into stars under such extreme pressure, and we can watch to see if the resulting stellar system remains gravitationally bound or if it flies apart. Each tiny green dot in the sky is a potential laboratory for the most dramatic act of cosmic construction, offering a front row seat to a process we once thought was lost to the deep past, the forging of immortal stellar cities from pure, chaotic energy. The final breath of a star is more than light, it is a forge for new worlds. As an aging giant star in a cluster enters its asymptotic phase, it begins to shed its outer layers in a slow, powerful wind. This expelled material, rich with newly forged elements like carbon, oxygen, and silicon, drifts into the cold of space. There, atoms begin to stick together, forming microscopic seeds. These seeds grow, layer by atom, into solid dust grains, the very building blocks of future planets and life. But infrared telescopes have peered into these stellar winds within clusters and found a strange chemistry at work. The dust is not what we expect. Around these cluster giants, astronomers detect the spectral fingerprints of exotic compounds like aluminum oxide, known as alumina, and silicon carbide. These are refractory grains, materials that form at exceptionally high temperatures, like the ceramics in a kiln. Their prevalence is a direct clue to the unique conditions inside a star cluster. In the isolated death of a field star, the expanding envelope cools rapidly as it drifts into the emptiness. This allows for a wider variety of dust, including fluffy silicates and carbon-based soot. But in a cluster, the environment is far more hostile and crowded. The space between stars is not empty. It is filled with the combined radiation and stellar winds from thousands of neighbors. This creates a pervasive, intense radiation field that bathes the dying star's outflow. This external radiation acts like a relentless heat lamp, keeping the ejected material warmer for longer as it expands. In this warmer environment, only the toughest, most refractory grains can condense and survive. Alumina and silicon carbide form at temperatures of over 1,500 degrees Celsius, much hotter than where common silicate dust would appear. So the cluster itself is acting as a cosmic filter, selectively permitting only the most durable stardust to form around its elderly members. This dust is not merely a curiosity, it is a time capsule with two histories. First, it records the internal nuclear processes of the specific star that made it. Silicon carbide grains, for instance, are a hallmark of carbon-rich stellar atmospheres. Second, and more profoundly, the dust's very existence and composition encode the environmental pressure of the star's home. The exotic grains we see are a direct product of the stellar city's collective glow, a literal piece of the cluster's ambient energy frozen into solid form. When these stars finally complete their transformation into white dwarfs, this hardy, refractory dust will be blown out into the cluster and beyond. It will become part of the raw material for any future generations of stars or planets that might form, seeding new systems with grains forged in the unique, radiant pressure cooker of an ancient stellar metropolis. Gravity is the ultimate sorter in a city of stars, and it works with a patient, ruthless efficiency. Over billions of years, a globular cluster does not remain a random mix, it stratifies. This is the phenomenon of mass segregation, a grand, slow-motion rearrangement where the stellar metropolis organizes itself by weight. Heavier stars, the brilliant blue giants, and the dense stellar remnants like neutron stars gradually sink toward the bustling city center. Meanwhile, the lighter, redder, sun-like stars are nudged outward, drifting toward the quieter suburbs and halo of the cluster. The driving force behind this cosmic migration is a process called dynamical friction, a kind of gravitational drag. Imagine a massive star moving through a sea of lighter stars. Its powerful gravity creates a wake behind it, a slight overdensity of stars pulled along in its path. This wake, in turn, exerts a gentle but persistent gravitational tug backward on the massive star, slowing it down. It is like wading through a dense crowd. Your progress is constantly impeded. This loss of energy causes the massive star's orbit to decay, spiraling it inward toward the cluster's core. The lighter stars, conversely, experience the opposite. Through countless gravitational interactions, they tend to gain energy, boosting them into higher, wider orbits that take them farther from the dense center. Computer simulations of this process are breathtaking to watch. They begin with stars of all masses scattered evenly throughout a spherical cluster, a chaotic but uniform swarm. As the virtual clock advances millions of years with each second, a pattern emerges. The bright, heavy points begin a slow, stately drift inward, congregating in the central regions. The fainter, lighter dots are progressively scattered outward, forming a diffuse halo. The core becomes a glittering, dense knot of massive stars and stellar corpses, while the outskirts become a realm of ancient, frugal red suns. This relentless sorting has a profound and potentially catastrophic consequence. It sets the stage for core collapse. As more and more mass concentrates in the center, the core's density skyrockets. The gravitational pull in that central region becomes overwhelmingly intense. In the most extreme cases, this can lead to a runaway instability where stars in the core interact so violently and so frequently that they either merge in catastrophic collisions or are flung out of the cluster entirely at tremendous speeds. This process can, in theory, lead to a moment where the core suddenly and catastrophically contracts, a gravitational collapse that further amplifies the density and chaos. Not all clusters experience a full collapse. Many are stabilized by other factors, like binary stars acting as energy sinks or the presence of a central black hole. But mass segregation is the inexorable engine that drives them toward that brink. It means the serene, ancient globe of light we see in our telescopes is not a frozen snapshot, but a system in a constant, slow-motion dance toward equilibrium. A dance where weight determines your place in the stellar city, and where the center grows ever denser, ever more brilliant, and ever more volatile with the passage of cosmic time. A globular cluster's journey is a perpetual plunge through the galaxy's invisible sea of gravity, and that voyage is far from smooth. Every time one of these ancient stellar cities passes through the dense plane of the Milky Way's disk or swings perilously close to the galactic bulge, it experiences a gravitational jolt of immense proportions, a tidal shock. This is not a gentle tide, but a sudden, violent tremor that runs through the entire cluster. The effect is called tidal shock heating, and it fundamentally reshapes the cluster's destiny. Imagine the cluster as a vast, spherical swarm of bees. As it plunges through the galactic disk, the stars on the side nearer to the dense plane feel a sharply stronger gravitational pull than the stars on the far side. This difference in force does not stretch the cluster slowly. It delivers a sudden, collective kick to every star in the system. The stars receive a burst of energy, like a crowd being jostled all at once. This injection of energy does not make the stars hotter in temperature, but it makes their orbits more energetic and chaotic. They begin to move faster and on more elongated paths, effectively puffing up the entire cluster. The cluster's outer regions, where gravity's grip is weakest, suffer the most. Stars there receive the biggest relative kick, and many gain just enough energy to escape the cluster's gravitational hold entirely. With each passage through the disk or close encounter with the bulge, the cluster loses more of its outermost citizens, its halo of stars steadily eroded away. This process acts as a powerful counterforce to the inward drag of mass segregation. While gravity is trying to concentrate mass in the core, tidal shocks are trying to blow the cluster apart from the outside. The cluster's long-term survival becomes a balancing act between these two titanic forces. A cluster on a plunging orbit that takes it frequently through the galactic plane will be subjected to these shocks on a regular schedule, perhaps every 100 million years. Over the 10 billion year lifetime of a cluster, this adds up to 100 such violent events. Each shock strips away stars and inflates the cluster's size, making it appear more diffuse and extended than its sheltered cousins in the galactic halo. This is why we see such a variety of shapes and densities among globular clusters. Their structure is a living record of their orbital history. A tight, compact cluster likely orbits far from the galactic plane, safe from frequent shocks. A puffed-up, diffuse cluster with long tidal tails is a veteran of the disk wars, its form shaped by repeated gravitational battering. This heating mechanism even sets a lifespan. For some clusters on the most extreme orbits, tidal shock heating may be the dominant process that ultimately dissolves them, scattering their stars into the galactic halo faster than any other mechanism. Their brilliant light is not eternal, it is a clock ticking down with every perilous passage through the heart of their own galaxy. Even the most orderly stellar diagrams hide startling anomalies. On the classic Hertzsprung-Russell plot, which maps a star's color against its brightness, astronomers have long recognized a distinct region called the horizontal branch. This is where old, sun-like stars reside after their red giant phase, burning helium in their cores. The hotter, bluer end of this branch is populated by stars that have lost a significant amount of their outer mass. But in certain clusters, this blue end does not simply stop. It curves sharply upward and backward, creating a distinctive hook shape filled with stars that are far hotter and more luminous than any standard horizontal branch star should be. These are the blue hook stars, and their position on the diagram is a flagrant violation of the standard evolutionary track. A star cannot naturally evolve to that extreme location through normal, solitary aging. Their existence demands a more exotic and dramatic origin story. The leading theory involves a cataclysm known as a late helium flash. Picture a star that has already left the red giant branch and is quietly descending toward the white dwarf graveyard. Its core is a degenerate ball of helium and carbon, too cool to ignite fusion. But then, in a final, violent spasm, something triggers a runaway thermonuclear explosion right in that inert core. The helium flash, which normally occurs smoothly at the tip of the red giant branch, happens here with catastrophic suddenness in the degenerate matter. This late, violent ignition does not destroy the star, but violently reheats it, blasting away additional outer layers and exposing an even hotter interior. The star is violently thrust back onto the Hertzsprung-Russell diagram, but now at a position far bluer and brighter than before, creating that hooked trajectory. Another compelling path to this extreme state involves the gravitational drama of a binary system. If two low-mass white dwarfs in a tight orbit spiral together and merge, the combined object can reignite helium fusion in its core. This stellar resurrection creates a single, rejuvenated star with the mass and heat to shoot far into the blue hook region. These stars are not quietly aging, they are cosmic phoenixes, resurrected by either a last-minute internal detonation or a violent merger. Their intense ultraviolet light dramatically affects the energy balance of their host cluster, and their very presence forces us to acknowledge that a star's path to its final rest is not a single, straight line, but a potential maze of resets, explosions, and second chances written in searing blue light. Brown dwarfs are the cosmic in-between, objects too massive to be planets yet too small to ignite sustained fusion in their cores. They are failed stars, destined to glow faintly with the residual heat of their formation before fading into darkness. In the rich stellar nurseries of star clusters, we would expect to find them in abundance, the smaller, cooler siblings to the brilliant suns. Yet in certain clusters, they are conspicuously absent. This missing population presents a quiet but significant mystery. Are brown dwarfs bad at forming in clusters, or are they simply not welcome to stay? The first possibility points to a flaw in the recipe. The formation of a brown dwarf requires a collapsing cloud fragment to have just enough mass to begin the journey of a star. but not enough to cross the critical threshold of about 8% of our Sun's mass needed to fuse hydrogen. In the turbulent, competitive environment of a young cluster, the process of building stars might be biased toward making either proper stars or tiny planetary mass objects, skipping the middle ground. Perhaps the intense radiation from massive newborn stars in a cluster evaporates the dusty envelopes around the smallest protostars before they can fully accumulate mass, stunting their growth and leaving a deficit of brown dwarfs. It is a cosmic assembly line that favors the very large and the very small, with little output in the middle. But the second possibility is one of gravitational prejudice. Brown dwarfs, while more massive than planets, are still the lightweights of the stellar city. In the relentless dynamical environment of a cluster, where gravitational interactions constantly reshuffle the stellar population, the least massive objects are the most vulnerable. Through countless gentle gravitational nudges from more massive stars, brown dwarfs can be steadily given extra kinetic energy. Over hundreds of millions of years, this process can boost them to escape velocity, ejecting them from the cluster entirely. They become cosmic drifters wandering the galaxy alone, their origin in a dense cluster untraceable. This dynamic ejection would act as a slow but efficient filter, cleansing the cluster of its faintest members. The clusters we see today, then, would be the survivors of this gravitational pruning, their populations skewed toward stars hefty enough to withstand the constant pushing and pulling of life in a crowded metropolis. To distinguish between these stories, a birth defect or an eviction notice, astronomers look for clues in the cluster's current state. If brown dwarfs were never made, the cluster's initial mass function, the ledger of how many objects of each mass were born, would show a dip specifically at the brown dwarf range. If they were ejected, we might find an excess of free-floating brown dwarfs in the general galactic field near the cluster's orbit, the exiled population still lingering in the neighborhood. The answer likely involves both narratives, a combination of formation physics and dynamical prejudice that leaves our oldest stellar cities curiously lacking in these twilight objects. Their absence is a subtle signature, a demographic silence that speaks volumes about the harsh social dynamics and the precise conditions of star formation in the universe's most prolific factories. A cluster is not a monolithic city, but a place where neighborhoods remember their origins. The search for substructure, for smaller bound groups of stars within the larger cluster, is a hunt for the fossilized scaffolding of its chaotic birth. This is the idea of a star cluster within a star cluster. If a globular cluster formed from the merger of several smaller stellar groups, or if it collapsed from a particularly lumpy giant molecular cloud, the stars from those original, denser clumps might remain loosely associated for billions of years. They would move together through the larger cluster like a school of fish within a vast ocean current, a subtle imprint of the initial construction. Finding such substructure is incredibly difficult. Over eons, the relentless gravitational interactions between stars, the process we call relaxation, should erase these primordial patterns, smoothing the cluster into a uniform, spherical swarm. Yet, hints persist. In some clusters, advanced statistical analysis of stellar positions and motions reveals faint, residual clumping. Stars are not perfectly evenly distributed. There are slight overdensities, groups of stars that share a common motion distinct from the smooth flow of the cluster as a whole. It is like listening to a symphony and picking out a single violin section that is playing a slightly different, older melody beneath the main harmony. The most promising place to look for this fossil hierarchy is in the cluster's outer halo, where stellar encounters are less frequent and memories can persist longer. If confirmed, such substructure would be a direct window into the cluster's violent infancy. It would tell us the cluster was not born in a single, smooth collapse, but was assembled from smaller pieces, like a galactic city that grew by annexing surrounding towns. Each of these stellar neighborhoods would carry a slightly different chemical signature, a subtle variation in the story told by the multiple populations. The hunt for these internal clusters is a testament to our desire to read the opening chapter of a story 10 billion years old, to see the blueprint from which the grand, ancient city was built. The final discovery brings us back to the very particles that scream through the void. From specific directions in the sky, Earth is bombarded by an intense, localized rain of the most energetic particles in the universe, cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, accelerated to velocities infinitesimally close to the speed of light. They carry energies so vast that a single particle can rival the force of a professionally thrown baseball, all packed into a subatomic speck. When scientists mapped the arrival directions of these ultra-high energy cosmic rays, they noticed a curious pattern, a statistical excess, a hotspot, that seemed to align not with a single star or galaxy, but with the general vicinity of a dense globular cluster. This correlation sparks a profound debate. Could these ancient cities of stars be natural, gargantuan particle accelerators? The challenge is that cosmic rays are electrically charged. As they travel across millions of light years, their paths are twisted and scrambled by the Milky Way's magnetic fields, making it impossible to trace a single particle back to its exact source. We see only a blurred statistical hint, a slight concentration of arrivals from a patch of sky. But if the link is real, the implications are staggering. What process inside a globular cluster could possibly launch atomic nuclei to such impossible speeds? The prime suspect returns us to the violent objects we have already met, pulsars. A rapidly spinning neutron star with its unimaginably strong magnetic field is a perfect cosmic dynamo. Charged particles can get caught in these magnetic fields near the pulsar's poles and be whipped around, gaining tremendous energy before being flung out into space like a stone from a sling. This process, known as magnetospheric acceleration, could potentially produce cosmic rays of moderate to high energy. But to reach the ultra-high energies we see in the hotspots, something even more extreme is needed. This is where the cluster environment itself becomes critical. A single pulsar might not be enough, but a cluster core could contain dozens or even hundreds of these spinning magnets. The combined effect could create a turbulent, magnetized region where particles are not just accelerated once, but repeatedly. A cosmic ray proton could be bounced from the magnetic shock front of one pulsar wind to another, gaining a little more energy with each encounter, a process called stochastic acceleration. It would be like a pinball being passed between 100 increasingly powerful bumpers, each one sending it flying faster until it finally escapes the cluster at nearly the speed of light. Another possibility involves the remnants of ancient supernova within the cluster. The expanding shock waves from these past explosions could also serve as giant accelerators, surfing particles to extreme energies over millennia. The hotspots, if confirmed, would crown globular clusters with a final, invisible halo of ferocious power. They would no longer be merely collections of stars, but integrated engines that take the raw stuff of atoms and forge them into relativistic bullets, firing them across the galaxy. This potential role transforms them from passive celestial landmarks into active, shaping forces in the galactic ecosystem. Their influence felt not just in light, but in a relentless, invisible rain that has been falling on our world since long before life began. From the ghostly whisper of gravitational waves to the violent birth of hypervelocity stars, our journey through 50 strange discoveries reveals a universe that is infinitely more dynamic and mysterious than we ever imagined. These star clusters, once dismissed as simple, ancient fossils, are in truth the cosmos's most enduring and complex laboratories. Within their glittering cities, the fundamental rules of physics are stretched, broken, and rewritten. They are factories for cosmic monsters, archives of galactic cannibalism, and forges for the very atoms that make up our world. Each paradox, from the missing lithium to the polluted stellar generations, is not a dead end, but a signpost pointing toward a deeper layer of reality we have yet to understand. These ancient gatherings of light are active, breathing entities that continue to shape the galaxy and challenge everything we think we know. So the next time you gaze at a faint, fuzzy patch in the night sky through binoculars or a small telescope, remember you are not looking at a static ornament. You are witnessing a living metropolis, a billion-year-old engine of creation and destruction whose secrets are only beginning to unfold. Which of these 50 discoveries reshaped your view of the cosmos the most? Let us know in the comments below. If you enjoyed this voyage to the edge of understanding, subscribe and ring the bell for more journeys into the deepest cosmic mysteries. And tonight, step outside, look up, and see the ancient, brilliant cities of stars not as distant points of light, but as the restless, beating hearts of a universe